All right, so now we're on chapter 10. And so you may remember from last time, earlier on late in the first semester of your chemistry experience, you did some gases. This is actually sort of an extension of that, where we're talking about the liquids and solids in greater detail for the three phases of matter, which are gas, liquid, solid. So you're going to realize pretty quick here that we're actually going into greater depth on many of the things you actually learned back in the first semester, probably towards the very beginning, depending on which book you used, which class where you took the class. It may have been like chapter 3, 4, that sort of thing. So you'll realize that pretty quick that you're having to go back in your brain and remember things that are a little old. So I'll try to review where I can, but I don't have the ability to make this into, a 3, 4 chapter long thing. Okay, so right here's our table of contents again, likewise. You may remember that we have three states of matter we talk about. These are the three primary states of matter. There theoretically are other states of matter, but these are the ones that are important on Earth, so we talk about these. Now, gases, liquids, and solids are these three states of matter. And the important things to remember is the gases are far apart, moving rapidly, they don't interact a lot. They're the highest energy state of the matter. Liquid is going to have, if this was zero connections, this is going to be something like 20% connection. And so about 20% of these will actually be connected together, and these connections sort of shift back and forth, letting these slide among each other, and that's what a liquid is. Much, much more dense, as you can see. And then a solid is going to have, if this was 20%, this is going to be something like near 100% connections. Typically well above 80%. Now, this right here, they are going to be even more densely packed, usually. That's not true for all of them. And they're going to have a much more rigid structure. This is why it does not flow, whereas liquids flow. All right, so intramolecular bonding. One of the things you can remember for remembering intramolecular versus intermolecular bonding that we're going to be talking about is when we talk about interstates, that means you're traveling between states. And so, as in the roads that you drive along, interstate. Intermolecular bonding is going to be bonds that happen between molecules, okay? Not within the molecules. Much like an internet connects us all across the globe among different computer networks. An intranet is actually what you have inside your school or inside of your home. Those are intranets, okay? So intramolecular bonding, these are going to occur within the molecules. Those are the normal types of bonds that we've went through. We actually talked in greater detail just last chapter, right? The condensed states of matter are going to be the ones that are condensed. They are together, right? They are more dense. And so those are going to be liquids and solids. These state of matter and these connections that are going to cause these states of matter are actually going to be certain forces that we need to talk about. So the intramolecular bonding, these are things like covalent bonding and ionic bonding. The intermolecular bonding, these are going to occur between the molecules. So not inside of a molecule, but between two different molecules. And there are several different types of intermolecular bonding. I may go into a bit, but I want to cover a bit more material before we go into that. So the first thing is the changes in state. So when a substance changes from solid to liquid to gas, the molecules are going to remain intact. You are not breaking those molecules apart. Just like if you have water, you melt it from ice to liquid and then liquid to gas, it doesn't suddenly become hydrogen peroxide or methane. It stays water. And that's because the intramolecular bonds are not disturbed. The intermolecular bonds are the ones you're breaking, going from solid to liquid. You break about 20% of them. Going from liquid to gas, you break about the remaining 80%, and that gives you the individual water molecules flying around in space. All right, now these are going to be caused by changes in the forces among the molecules, not within the molecules. You need to catch on to that and remember that and have that in the back of your head every time you're doing something in this chapter. And really, anytime you're doing anything with chemistry or biology, you need to understand this. So, when energy is added to ice, what happens is, much like when you start smashing something with a hammer, you're going to start breaking pieces of it off. And so when you add energy to ice, you're literally breaking apart some of the bonds. If you break apart enough of the bonds, you're going to cause that water molecule to start flowing. And this is going to change the structure and give you water, liquid water. So this increased energy is going to result in greater movement, a greater disorder, and this is going to be characteristics of liquid water, which is going to be partially disordered, mobile water molecules. Notice I said partially disordered, by the way. An interesting new piece of information that they came up and found out within the last 10-20 years and has had a lot more research is, as it turns out, liquids actually have little pockets of order. So it's actually like little pockets of order, and then a few of those molecules are somewhat loose and can move around among these little pockets of order. And that's actually what liquids are. It's kind of an interesting thing. But when more energy is then added to that liquid water, well, what would you expect? So I have water on the burner. I start off with ice, it melts, and then the next thing it does is, well, it's going to go to gas, right? And so as you put more energy in, it's going to go to the gaseous state eventually. And that is going to cause these intermolecular distances to vastly increase. And they're going to go so far apart that the individual molecules are essentially not interacting at all, if they are at all. In the case of water, they do interact a little bit if they happen to get close enough to each other. If you have a big enough container, they won't interact at all because they will separate so far they won't be able to. So the intermolecular interactions are much, much lower in a gas. Almost negligible, but not quite for everything. So more energy is required to overcome the covalent bonds and decompose the water molecules into their component atoms. You can do that. That's actually how the you may have seen them, but maybe not. It depends. There is actually something called hydrogen fuel cell, or hydrogen gas being made from different energy processes, and that's how then they store the energy. That's actually what they're doing there. They're decomposing the water molecules into the component atoms. One of the ways you can always remember this is you probably have boiled water in your house before. And so when you're boiling water, you are doing this process that I talked about before, changing the states, right? But you'll notice that you've probably never been boiling water and suddenly there's a loud explosion because hydrogen gas and oxygen gas lit and blew up. And that's because you've never reached the energy that is needed to decompose the water molecules. And so you should have realized this in your life before, that it takes a lot more energy to decompose water molecules. It takes a lot more energy than boiling to cause a chemical reaction. And so typically the difference, the sort of order of magnitude difference when you're talking about intermolecular interactions versus intramolecular bonds is like a factor of 10. Okay, you would need about 10 times the amount of energy to start breaking intramolecular bonds as you would intermolecular bonds. And so that's a pretty good generalized factor. So right here, we're going to cover some of the intermolecular forces. So first, we're going to start with dipole-dipole forces. Now you should notice, take note, that almost everything I do and say has a meaning to it. There's a reason for everything I do and say with you guys. I don't typically give you useless information that you don't need to know or won't help you in some way. And so, for example, even the order I do things matters. So, dipole-dipole forces is the first thing I give you for the intermolecular forces. And the reason for that is it is the weakest, but it is also in every single one of the other, it is one of the most important ones we're going to talk about. So, it is not in everything, but it is one of the middle ones, okay? And we need to understand these dipole-dipole forces because there's going to be another one that, frankly, it is just dipole-dipole forces. Anyways, forces that act between polar molecules or dipole-dipole forces. Another thing you should take note of on chemistry, and it's not true for a lot of the other sciences, but it is true for chemistry, is that the names always mean what they are. Okay, if you really read the name and truly thought about it a little bit, you actually probably would not need definitions. I know I didn't. Oftentimes, to be honest, in full disclosure, I was a truly awful student. Okay, if I had to teach myself, I would be very, very angry and not happy with me. Because I did not study. I did not do studying at all, and I would just work out the equations. I wouldn't even write them down. I would just work them out from the constants when I grabbed the exam. And I had to spend about 10 minutes doing that, and then I'd answer the questions in 15. I'd still get out there early. So I was not a good student. Don't do that. Anyways, if you look at the dipole-dipole forces, this gives you a huge hint. Di-2 poles, so that's positive negative pole interacting with another positive negative pole. And from the previous information, you should be able to deduce that, hey, that is a positive attracted to a negative on another dipole. Okay? It's essentially two magnets clicking together, right? And that is pretty much what a dipole-dipole force or dipole-dipole attraction is. So you're going to have two polar molecules. Notice they have to have a dipole. That means a positive side and a negative side. If they don't have an overall positive and overall negative side, this is not going to work out. Okay? So dipole-dipole attraction, definition, is electrostatic attraction between molecules with dipole moments. Dipole moments is just a fancy way, in your guys' case, up to this point, of saying it has a dipole at that given moment, or it has a dipole, okay? If you want to know more about it, it's very important if you start going into spectroscopy, and if you start going into advanced chemistries, and even advanced biochemistry, this becomes more and more important. This is actually what causes things to be able to pick up microwaves, by the way, if you're curious. This is what microwaving your food uses, if you're curious. Dipole moments are important there. And spectroscopy for like global warming, infrared being absorbed by the atmosphere. That's also what's happening there. It's the dipole moments that are acting. But anyways, think of it as a positive and negative charge at any given moment. So the molecules will always orient themselves in a way where the positive and negative ends are going to be close to each other. Think of it this way. If you get a positive next to a positive, they'll repel, and one of them will end up flipping, or both of them will flip. And therefore give you your negative attracted to the positive. And that's the lowest energy position that will end up being the overall positions. So in a condensed state, the dipoles will find the best compromise between the attractions and repulsions. again, you have more than just attraction and repulsion going on here. So when you have your positive negative ends next to each other, there's going to be the best angle, right? You may have noticed that if you just throw a bunch of magnets onto a table and then start scooping them together, some of them will flip, so the positive is next to the negative. Some of them will orient. Notice if you put two magnets next to each other, they will snap to the strongest attraction, right? The best compromise between the attracting and repulsing forces, which typically is the broad flat side of the magnet, but you get what I'm talking about, hopefully. If you don't understand what I'm talking about, please just go to a store, grab some cheap nickel magnets. They literally cost a few cents each, and just play with them a little bit. Okay? All right, so I forgot where I was here because I got interrupted by a call. But, all right, I think I covered this slide, hopefully. If I didn't, please leave me a message and I'll come back and do something. All right, so the characteristics of dipole-dipole forces, approximately 1% as strong as a covalent or ionic bond. So those would be your intramolecular forces. This is only 1% as strong as those intramolecular forces, on average in this case. The strength of the forces decreases as your distance between the dipoles increase. I know it's a little bit long saying. If you played with magnets, you'll notice when they're a foot apart, you can't even feel them attracting, right? And that's what you're experiencing. That is the same electrostatic attraction that we're looking at here. It's literally just positive, negative sides of magnets. When they're far apart, they have very little attraction or repulsion. As they get closer together, they'll experience more and more attraction and repulsion. This is a great diagram to understand this sentence right here. In a condensed state, dipoles find the best compromise between attraction and repulsion. So you'll see here that these magnets have attractions going on between the positive and negative ends. And then they have repulsions going on between the negative and the positive and positive ends. What that means is you can't just shove all of them as close together as possible so they're touching each other. First off, you can't even get them touching each other because remember, these are molecules. They all are surrounded by electrons. If you tried to shove them into each other, the electrons would start repelling. And that's actually what you experience when you touch things, if you're curious. You don't actually come in contact with what you touch. You experience the electrons of your atoms repelling the electrons of the desk, chair, whatever you're trying to touch right now. All right, so in this case, we have this is going to try coming as close as possible to this negative charge here. This is going to try to come as close as possible to positive charges, but it's not going to get right up on it because these other positives will repel this one. So you're going to end up having a best compromise structure, and that's really what you get for these structures. So keep that in mind. All right, so the next one I'm going to do here is hydrogen bonding. The reason this is the next one after dipole-dipole forces is because there isn't actually any difference. We have a false difference, if you will, or we've taken a very select portion of the dipole-dipole forces and we have put them in their own category, hydrogen bonding. And we have done that because water, probably the thing that all life depends on, and we are a life form, does hydrogen bonding. And so we consider hydrogen bonding to be extremely important, and to us it is. It is incredibly important, and so we have put its own category. Now, this is just a very, very strong dipole-dipole force. So it's just very strong dipole-dipole attractions. They're going to, by definition, have hydrogen involved. So you're going to have a hydrogen atom bound to a highly electronegative atom. Well, again, what are the highly electronegative atoms? Well, they are the ones in the top right of the periodic table. So this is going to be hydrogen bound to chlorine, fluorine, oxygen, and nitrogen are typically what these are defined as. Is they're going to be hydrogen bound to those four atoms, one of those four atoms. And those will make very, very strong, very small, that they can interact very closely, magnets, if you will. Which means that these dipole-dipole forces are much stronger than they normally would be. Now, you can actually have hydrogen bonding that happens with hydrogen bound things that are not those four atoms that I discussed, but that's sort of an advanced topic. We're going to not go into that. And honestly speaking, I would be surprised if you encounter anything that is not one of those four. That would be very, very shocking, actually. So this has causative factors, of course. There's the polarity of the bond. Because of the large difference in electronegativity, the hydrogen is extremely positive in these, almost an ion, but not quite. The electronegative atom is going to then be very negative, not quite an ion, but close. The proximity of the dipoles is a big factor here. Now, the special sauce, if you will, of these hydrogen bonds is the fact that the hydrogen atom is already very, very small. Once you make it slightly positive charged, it's going to become even smaller. And so that means that you have two, a positive and negative charge, that are fairly small and fairly close together. And so these can get shoved into areas that larger dipoles could not, and they can make much closer interactions than larger dipole molecules can. This is going to influence the physical properties of these molecules, making them have things like much higher boiling points, much higher melting points, higher viscosities, that sort of stuff. So right here we see a water molecule, and this is the stereotypical hydrogen bonding because, frankly speaking, it's just probably the single most important molecule to living organisms, period. We have never found anything that's alive that does not depend on water to live. Now, this right here is going to be the negative charge. It's on the oxygen. Right here we have a positive charge that's over here on the side with the hydrogens. Each of the hydrogens is going to have what is called a partial positive charge. By the way, if you've ever wondered why you have this small delta as the symbol, small delta positive, small delta negative, literally small delta means a part of a whole. And so you have a not a plus something slightly less than one charge. You have a something less than a negative one charge here because these are not ions, right? They don't lose their electrons. And that's why you get that partial positive, partial negative. Right here then we have how water molecules would connect. Notice they make sort of little cluster shapes. And so you have the positive hydrogen that's going to interact with the negative oxygen. And here we have the positive hydrogen that's going to interact with that negative oxygen. And they line up like so, positive to negative, just like dipole-dipole interactions. They're just stronger, closer together. All right, so here's some boiling points for covalent hydrides of our elements. They're in group 4, 6, and 7, and 5. So, got out of order there. Right here's group 4. Right here's the one in group 5. This is 7, and this is 6 right here. And what you will see is that as you go down the group, the electronegativities trail off. And so what you get is, right here we have hydrogen bonding. Those are all hydrogen bonding. They're very strong, so the boiling point is very, very high because you have to break apart very strong intermolecular interactions. Right here, we have no hydrogen bonding. This is a nonpolar compound. It doesn't have an overall dipole. And so we have the lowest boiling point right here. This is actually a gas at room temperature. The next one up, we start seeing a dipole-dipole interactions here. And so our dipole-dipole interactions have higher boiling points. The next one up, we actually start seeing the effect of just having heavier and heavier atoms. And that's true for everything. Everything experiences this, that the higher the weight, the more interactions you have. And we'll talk about those in just a bit. They're called London dispersion forces, which is the next one we're doing. And so you may have looked at this and went, "Oh, wait a second. These seem like the reverse of what's happening. You have less and less dipoles, smaller and smaller dipoles, worse and worse magnets, weaker and weaker magnets." So these, yes, you actually have somewhat less dipole-dipole interactions. Not huge as much as you might think, but they are less. Here we're seeing very strong dipole-dipole interactions. And what's going on there, why that boiling point keeps increasing, despite the fact that the dipole interactions are actually going down, is that we're getting more and more London dispersion forces. Now, London dispersion forces, while being the weakest of the forces I'm talking about here, are actually one of the most important ones as well. And that's because these are the forces that actually exist among all molecules. Okay? Every single set of molecules you have together has London dispersion forces all the time. All right? These are going to be the forces that are going to keep noble gas atoms and allow them to be liquid. These are also the ones that are going to allow nonpolar molecules to be a liquid or solid, because they'll happen there, and they are the only forces that are happening in nonpolar molecules and noble gas atoms, the only intermolecular forces that are occurring. What they are is London dispersion forces are going to be accidental, instantaneous dipoles that are going to occur in an atom. These are going to induce similar dipoles in neighboring atoms. What this is going to end up leading to is very short interatomic interactions or attractions. These are weak, they're short-lived, but if you have a large enough atom or a molecule, you are going to start seeing more and more of these interactions. So the big factors here that are going to matter most is going to be, well, polarizability is going to matter a lot in these. And polarizability indicates the ease with which the electron cloud of an atom can be distorted to give a dipolar charge distribution. Think of it like this. You remember how I kept pointing out and talking about, and your previous professor kept pointing out and talking about how the electrons happen in wave probabilities. They don't orbit around the nuclei in nice patterns. They actually pop in and out of existence all around in those orbitals. So you have a randomly moving electrons around your atom. Every now and then, those electrons are going to end up with more on the one side than the other. And what this is going to cause is you'll have a slightly negative charge where the electrons ended up more on one side, and you'll have a slightly positive charge on the other side where there's less electron density. And that means you have a temporary dipole, right? A momentary dipole, which is referred to here as an instantaneous dipole, and that is the correct language. All right, so when you form this instantaneous dipole, well, the electrons that are on the atom next to it are going to be attracted to that positive charge, right? And the electrons on the atom next to it that are next to the negative charge are actually going to be pushed away by those. And so what this can actually cause is this sort of swinging pendulum of positive and negative charges that end up lining up temporarily to give you an attraction. And this will happen randomly. You can induce it, but it is not something that is normally induced. However, it's going to happen more if you have something that has a lot of electrons or very loosely held, which is polarizability. If something has a lot of electrons and these electrons can very easily move around and very easily make a dipole charge distribution around that nucleus, then this is going to happen a lot more. So as the atomic number increases, as you have more electrons, typically you're going to be more polarizable, which means that you can have these temporary charge distributions, dipole charge distributions happen more often. This is going to increase the probability of having that momentary dipole interaction occur. This is used by all the nonpolar molecules to attract each other. One of the things I need to mention about London dispersion forces is I find this very useful for myself and for my students to envision these different forces as sort of strings and ropes, okay? And so London dispersion forces are like strings. They're small forces. They're very weak. If you try to climb up a building with it, it's probably going to snap and you die. But if you get enough strings, you can start climbing the building, can't you? Because enough strings will make it strong. So for example, you're trying to tie somebody down, or you're trying to tie your two hands together. If you just put one string, it's not going to work well, right? If you put 100 strings, it's going to be very strong. On the other hand, if we have something like a hydrogen bond, well, the hydrogen bond's like a rope. And so it's very strong in and of itself as compared to these London dispersion forces. And dipole-dipole interactions are typically much stronger in London dispersion forces as well, though not as strong as the hydrogen bonds. So we already have that sort of idea of a rope and string now. So what would happen if, say, somebody tied a rope to you and tied it to the desk, and then that same person went ahead and tied a string to you and tied it to that same desk? Would you care about the string? Would you talk about that string anymore? No, you'd completely forget about the string because there's a rope tied to you. You need to get rid of the rope, and then the string won't really matter that much, right? And so, typically when we have a dipole-dipole interaction or a hydrogen bond, we won't mention the London dispersion forces, despite the fact that London dispersion forces will still be there, they will still be acting, they are still a consideration, but they're just such a minor consideration compared to a dipole-dipole interaction or a hydrogen bond that typically they get ignored. So yes, remember that if you have something like water, hydrogen bonding is the most important by far and away. But it also has London dispersion forces, okay? All right, so chemical and physical changes at the macroscopic level. Now, you hopefully remember something about physical and chemical changes. So physical changes are going to be a change in the form of a substance, but not in its chemical composition. So, for example, you can pour water in two separate containers. You could boil water, but water is still water. It is not some other chemical compound like methane or hydrogen peroxide. Chemical changes, on the other hand, are going to be a change of a substance into other substances with different properties and different composition. So a chemical change is going to be changing methane to water. That would be burning it. Or it could be changing sugar into CO2, which is metabolizing it. Or burning it. That also is also burning. Apparently I'm in a mood for burning stuff. Alright, so how do you distinguish chemical and physical changes? These are going to be aided by molecular level perspectives. So a great example of this is phase changes. These are a type of physical change. Boiling water, of course, is going from liquid water to gaseous water. You'll take energy, you'll transfer it as heat, and that heat will cause these liquid molecules to separate from each other. Now notice you have not changed the intramolecular forces, which are the bonds between hydrogen and oxygen. You have only broken the intermolecular forces, which are the hydrogen bonds. And once you've overcome them, you have split your water molecules apart and gotten the gaseous form or water vapor. Alright, so let's do a chemical change. Right here we have the combustion of methane I mentioned before. So here's methane. We burn it in the presence of oxygen. We will get CO2, which is a different compound than these two. And we will get water, which again is a different compound than these two. So notice that we have broken intramolecular bonds that are the covalent bonds between carbon and hydrogen, and the covalent bond between the oxygens. And we have made new chemical bonds. So, dipole-induced dipole interaction. So a permanent dipole on a polar molecule can induce a dipole on a neighboring nonpolar molecule. This is another example of an intermolecular force. This is not quite as common as we've seen in the other ones, but it does occur in nature. The strength depends on the nature of both the polar molecule and the nonpolar molecule. So the larger the magnitude of the dipole in a polar molecule, the better able it is to induce a dipole in a neighboring molecule. This is not a super common intermolecular force, as you may pick up from the fact that we're talking about a polar molecule that is going to mix with a nonpolar molecule. Another way of thinking about this is cases where you actually could get gas and water or oil and water to mix. And oil and water actually do mix to a very, very tiny degree, but mostly we know them as not mixing, right? So again, this is nonpolar molecules with a greater number of electrons that have greater polarizability. We'll typically do these dipole-induced dipole interactions because they're easy to induce a dipole on. Alright, so we have learned the difference between intermolecular forces and intramolecular forces at bonds at this point. What if the intermolecular force were stronger than intramolecular forces? So, for example, what would happen if you were to try to boil water? Well, if the intermolecular forces were stronger than the intramolecular forces, you would actually decompose or react the water before you could ever boil it. So instead of boiling water, you would actually cause an explosion. So you'd put your water in a kettle, put it on the burner, or you'd put it in the microwave, and you would blow up. You wouldn't get boiled water, would you? So that would be a big difference. Which one of the following is the strongest intermolecular force experienced by noble gases? So first off, you go noble gases. Well, those are nonpolar. And so those are going to experience London dispersion forces. They're not going to have the dipole-dipole hydrogen bonding or ion-ion interactions. The ion-ion interactions, by the way, are what is in salts, and we'll mention that when we get to the solids. Methane is a gas, but carbon tetrachloride is a liquid at room conditions, or room temperature. Which of the following statements explains this phenomenon? So we go through and see which one will actually make some sort of sense. Cl4 is a polar molecule and CH4 is not. Well, neither of these are polar molecules if you remember doing their Lewis structures and figuring out the poles for them. Otherwise, you could have realized that these both have carbon in the middle and they both have 4 things attached, so they're going to cancel out either way. CCl4 and CH4 have different geometries and shapes. Well, no, they do not. They both have carbon in the middle, and they have 4 chlorines around it, making a tetrahedral shape. CH4 exhibits hydrogen bonding, and CCl4 does not. Well, no, they don't have large differences in their electronegativities, do they? In fact, this is one of the stereotypical examples that keeps being given to you of something that's nonpolar. So hopefully you realize that that doesn't do hydrogen bonding by now. Cl is more electronegative than hydrogen. Well, it's not going to really matter that much here because this is just around this in a shell. This doesn't have an overall dipole, does it? And we kept mentioning that we need overall dipoles. So it's actually none of these statements is correct. The correct answer actually would be the mass. So again, when we have something that's nonpolar, what are we looking at? Well, we're looking at London dispersion forces. And so the greater the molecular weight, the larger the London dispersion forces. The larger the atoms are, the larger the London dispersion forces. So this is a liquid at room temperature because it has greater London dispersion forces, because it just weighs more, has more electrons, have more area for these temporary dipole connections to occur. So which of the following species exhibits the strongest intermolecular forces? So we go through here, what we're really looking for is either an ion, something like a salt, which has a very high boiling point, or lacking that, we're looking for hydrogen bonding. Lacking that, we would then look for things like dipole-dipole interactions. But typically, we hit a hydrogen bond, and right here we do. That's water right there. That has the strongest intermolecular force. Excellent. What types of intermolecular forces are exhibited by methane? So hydrogen bonding and London dispersion forces? No, that definitely doesn't do hydrogen bonding. Hydrogen bonding? No. Dipole? No. So we're left with London dispersion forces, and yes, that does London dispersion forces. Everything does. This just doesn't have anything else it can do. When a water molecule forms a hydrogen bond with another water molecule, which atoms are involved in the interaction? So we're looking for hydrogen interacting with oxygen in the water, right? And so we go through, bing, 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 and we find out it is C, which is a hydrogen atom from one water molecule and an oxygen atom from the other water molecule. Which of the following has the highest boiling point? So again, we sort of go through the order, and what we're looking at is these all have intermolecular interactions. In these cases, they're hydrogen bonds actually, so they're fairly strong. But down here, we actually have something that has intramolecular interactions, which are usually on the order of 10 to 100 times stronger. And so that is because those are actually ionic bonds, in this case down here, aren't they? That's a salt. And so that's going to be the strongest by a very, very large margin. By the way, salts typically have melting points in the 400 degrees Celsius range. The boiling point of water, which is the highest one here, has a boiling point of 100 degrees Celsius and a melting point of 0. So that's a huge difference. Which intermolecular force below is the strongest? So are dipole-dipole forces, London dispersion forces, or hydrogen bonds stronger? Well, if you remember anything from this lecture, hopefully you remember hydrogen bonds are stronger. There you go. Which of the following compounds has the lowest boiling points? And so we're going through here, and we're going, well, okay, these are all nonpolar. See that? They're carbon and hydrogens, all of them. They're very similar. So that means that what we're really looking at is those guidelines that were within the London dispersion forces. And that is that the more molecular weight, the higher the boiling point. The lower the molecular weight, the lower the boiling point. And so we're looking at the smallest one possible, which is that one right there, and that has the lowest boiling point. By the way, many of these questions you really can just do with some logic. I mean, just general logic. Uh, I have a kind of funny story about general logic. I have given for like 4 years in a row on my General Chemistry 1 exams every time I teach it, or my Principles 1 chemistry exams, which are similar classes. Um, I give a question that is essentially what melts on a hot sidewalk, and then I put things like ice cream, chalk. I always put chalk, and then water, ice, etc. And every single time, I get about half the students at minimum, at best, that will not put that will put chalk. They'll think chalk melts, or they will think that they will get for some reason they get tripped out. So just use some simple logic when you think about these. I mean, many of these things you've experienced in your life, right? So water, you have experience with that. You know, carbon monoxide and helium gas are in balloons, and natural gas that comes out of your stove. Those all have to come apart easier. Water is a liquid at room temperature. You know that has stronger forces. You should be able to tell that just from general everyday experience. What has the highest boiling point? Well, salts, right? You've never melted a salt. You've never boiled a salt. So it has to have a higher boiling point than the gas you breathe every day, nitrogen, and water that you probably have boiled. And then you look at these, and well, here we have natural gas. Um, we have butane right there that's in lighter. That's why when you open a lighter, it has a gas that comes out. But you've never even seen the liquid form of natural gas, have you? However, you've seen butane, and this is like one of the components of gasoline that you get at a pump. And so yeah, that has to have the lowest boiling point right here because you can tell the trend just from the stuff that you've actually seen in your life. So again, you can of course use the stuff I've been teaching in this lecture, but many of these questions you can reduce down to one or two options just by using a little bit of common sense and logic. Just think about the things around you. So which of the following is the correct order of boiling points for CHOH? That's CH3OH. That's methanol, by the way. C2H6, ethane, and neon. And so we're trying to order these in lowest to highest. That's what that little symbol right there, the small part means lower. The larger part, the mouth, means higher, right? And so, first off, this is going to have the highest boiling point, right? Because that has an OH, that's hydrogen bonding. The next two that we need to look at, well, these are both going to be London dispersion forces. The neon is lighter than the C2H6, I believe. If you don't know, if you're not sure which one would be heavier and lighter, just look it up on a periodic table, okay? That's why I always give you excess periodic tables. And so, yes, it is neon, C2H6, methanol. Liquids. Now we are in liquids. Let me get a drink. All right. So we're going into liquids, more of a specific properties of those liquids that you probably think you know, but maybe don't know as well as you have previously thought. So liquids, these are going to possess low compressibility. You can compress liquids a little bit, but very, very little. You will notice once you start trying to, say, if you have a water bottle with you, squeeze the water bottle. It's the air part on top that really gets squeezed. Air, gas is very compressible. The liquid portion, once you try to start compressing that, it gets vastly more difficult and you have a lot of trouble doing it. Liquids are going to lack rigidity. What that means is that they pour, they flow. You can shape them, move them around. And they have high density as compared with gases. Gases have very, very low density. By the way, density is what dictates whether something floats or sinks in a gravity well like Earth. And so when you have lower density, it floats up. And when you have higher density, it goes downwards. And that's why liquids, i.e., the ocean, is below the atmosphere, which is gases. Surface tension. This is the resistance of a liquid to an increase in its surface area. Essentially, it says that if you take the surface of a liquid, you press on it, pressing on it would increase its surface area because it would indent, therefore increasing the surface area. And this is the surface tension that resists that. If you've ever done a belly flop or tried to do a high dive into water, that's surface tension working at its best. That's that painful plop that you experience. Surface tension is also, of course, what lets the water strider stride on water, which is an insect that can run atop water, because it's taking advantage of the surface tension of the water. Liquids with large intermolecular forces tend to have high surface tensions. Water has a pretty high surface tension. If you increase that intermolecular force by, say, adding in starch to the water, which can increase the intermolecular forces by water binding to the starch, you can actually run across water if you're very quick about it. You can look up videos for that if you'd like. I'll wait. All right, so polar liquids are going to exhibit capillary action. And capillary action is the spontaneous rising of a liquid in a narrow tube. If you've ever had your blood taken, you've experienced capillary action. Your blood is water-based, and they stick a small tube in you, and that water will slowly climb that capillary. If you've ever done like your diabetes blood sugar tests, those use capillary action. That's also why if you look at your straw in your cup, just a little bit, the liquid in the straw will actually be slightly higher than the cup if you look very closely. It works better the smaller the capillary, the smaller the tube. Anyways. Cohesive forces, these are going to be intermolecular forces among the molecules of the liquid. They're going to be what, first off, co as in same, similar. So cohesive, sticking together, same things. This is going to be a liquid like water sticking to water, right? Adhesive forces like glue, adhesive, is going to be sticking two things together. And so these are going to be the forces between the liquid molecules and the walls of the container. So this is a meniscus, and this is occurring because of the difference between the cohesive and adhesive forces in this container. So the adhesive forces between water and the silicates that make up glass are actually stronger than the cohesive forces between the water molecules. And so what happens is the adhesive forces causes the water molecules to build up along the edge of the silicates or the glass here. And then the adhesive forces are weaker, so they don't pull this water back down as much. And so you get this meniscus. By the way, one of the things you have to be careful of when you read meniscus is I oftentimes see people reading this forward edge as if it was the meniscus. The meniscus is actually in the middle of the container. It is the one in the middle, not the one closest to you. All right, right here, this is mercury, and this is another liquid. In this case, mercury is nonpolar, so it is not attracted to the glass. And so the adhesive forces are almost non-existent. The cohesive forces in mercury, however, are actually fairly strong. And so the mercury actually makes a reverse. See that? It's a convex meniscus. This is a concave meniscus. So concave going down, convex goes upwards. And that's because the mercury is actually more attracted to itself, other mercury. This is also why mercury beads, by the way. And if you've ever driven in a rainstorm, then you have experienced the wonders of the water having higher adhesive forces than cohesive forces. That's why the water, instead of beating up, when it hits your windshield, it sticks to your windshield and dribbles down it. If you use Rain-X or one of those other wipes or chemicals that you put on windshields to keep the water beating up, what that does is it actually lowers the adhesive force. Therefore, the cohesive force will be higher and it keeps the water beaded up, which means it rolls off. All right. Viscosity. So this is going to be the measure of a liquid's resistance to flow. Liquids with large intermolecular forces and complex molecules tend to be highly viscous. Okay, so large intermolecular forces are things like water typically has a higher viscosity than something, say, oil, that sort of thing. Many light oils. And that's because of the higher intermolecular force. The complex molecules, this is things like starch, or tar. Tar has a tremendously high viscosity, or syrup has a high viscosity because those are complex molecules. They're larger, and they tend to get wound into each other. Actually, the complex molecules are a little interesting and funny because it's actually a bit like when you have cords that you're carrying around in a sack. They get wound up with each other so you can't get them apart. Well, that's a bit like what complex molecules do and why they're highly viscous. Intermolecular forces, of course, just are going to be very strongly attached to each other. And if they're strongly attached to each other, they have difficulty coming apart and flowing, changing shapes. And so glycerol here has a very high viscosity. It's extremely viscous because it has 3 OH groups that can all hydrogen bond to each other. Very strong hydrogen bonding. Grease has low viscosity because it's nonpolar, has weak interactions, and this is a fairly small chain. There's actually kind of an interesting, it's a little sad but a little funny too. I guess it's Schadenfreude, which is the German word for enjoying people's misery. So apparently Germans had to come up with a word for that. Anyways, so there is a very prolific researcher who is out of Australia, and he had done a study to figure out the viscosity of tar. And this was originally initiated something like 70 years ago. And it was actually, at the time, a fairly important study because nobody had any idea if tar even dripped or anything. They weren't even entirely sure it was a liquid. There were a lot of opposing theories. So they did this study, and what it was is they have a container with tar in it, and essentially they just set it up and keep people watching it, and then they measure how long it takes to drip. And so the person that initiated the study, he missed it the first time. Somebody else caught it and recorded it, but he wasn't able to. And so they actually put this on a live feed, and it's on the internet. You can actually watch tar drip, though I would not recommend sitting there and trying to watch it the entire time because tar takes about 40 years to drip. And so this guy, he missed the first time. He managed to live long enough that they were getting close to the second time it should drip. And so he said, this time I need to see it. I set this up. It's been a lifelong thing for me. I should see it at least once, right? And so he stuck out there for a couple days. And when he went to go get his coffee, it dripped. So he missed it the second time, and he won't live long enough to get the third time, probably. So that's a sad thing, a little bit funny because, it's tar dripping, so I don't think he's going to be that inconsolable over it. But if you ever want to watch tar drip, it will take a while, but you can look it up online. Now, the structural model for liquids. They're going to have strong intermolecular forces and significant molecular motions. So think of them like uh, they have bonds between them, but not every single bonding point is bonded, so they can switch over back and forth, okay? They're more fluid, which, of course, liquid. They contain a large number of regions. The arrangement of the components are similar to those that are present in solid, but with more disorder, because solid has a much more set structure, more ordered structure. Holes are going to be present in a few regions. Regions are subject to rapid fluctuations and tend to change fairly quickly, which is why when you drip like food coloring onto a glass of liquid water, it rapidly goes and spreads throughout the glass. And that's because you have rapid fluctuations occurring. If you drip that same food color on solid water, you will notice it doesn't penetrate. It just, goes around it because it does not have fluctuations, at least not rapid fluctuations. So consider two liquids, A and B. Liquid A exhibits stronger intermolecular forces than liquid B. Which of the following statements is true? The surface tension and viscosity of liquid A are greater than those of liquid B. The surface tension of liquid A is greater than that of liquid B. The viscosity of liquid B is greater than that of liquid A. Well, honestly speaking, when it comes right down to it, you just really need to remember that these are all the same trend, right? So the surface tension and viscosity of liquid A exhibits stronger intermolecular forces. Okay, those both have the same trend, and then stronger means higher, are greater than that of liquid B. And so, of course, A has to be the correct one. Alright, so now we're into solids. So first off, we need to be able to classify these different solids. So the classification of solids goes, well, there's solids, of course, which is a phase of matter. And then we have different types of solids, which is the amorphous solids. And these have considerable disorder in their structures, though again, they are not completely disordered like some people think. They do have some degree of order usually. Crystalline solids are characterized by highly regular arrangement of components. They are extremely ordered. As far as I am aware, they are the most ordered form of matter. The positions of components in a crystalline solid is actually represented by lattices. If you've ever heard of lacing or lace, that's the same thing. Lattices are usually a framework in which you can define that pattern. So lattice, this is going to be in this case a three-dimensional system of points designating positions of components that make up the substance. A unit cell is going to be the smallest repeating unit of the lattice. So right here we see some unit cells and the lattices they create and an example of the substance that would make that. So here we have a simple cubic. It's simple because literally only the defining points of the lattice, see those edges, are the ones that have atoms on them. And so that is the unit cell, simple cubic. If you repeat that same pattern over and over, you can get the lattice right there. Now notice when we talk about these solids, these are going to be repeated patterns over and over. They are not going to end at just a nice little square like that, okay? They will keep expanding. We're just showing a small portion. So the polonium metal actually is one of the metals that would make a simple cubic, though these do not just define metals, they can define a variety of different substances, including salts, ionic compounds. And so here is body-centered cubic. It's the same thing as this, but there is one additional one in the middle there. See that in the middle? It's a little hard to see because this corner here is over here. There's the one in the middle, and there's the one that's closest to you. All right, so this is the face-centered cubic. It's almost impossible to tell what the hell's happening there. Literally, what it is it's the exactly what its name is. The naming for these are very straightforward. So simple cubic, literally all you've done is you have the atoms at the points, the vertices is what those are called, of the cube. Body centered, you have one in the center of the body as well. Face centered, well, you're going to have them centered on the faces of each face of the cube. See that? They'll be halfway in between each cube. So if we look here, you can see that this vertice, this atom here, there is a small portion of it in this cube on the left. There is another portion of it in this cube on the bottom right portion. See that? And so this atom is actually split among these cubes. The whole thing is not in a single cube. This one right here, the whole thing is in that center. So these faces, half of the atom would be in this cube, half of it would be in the next cube. So keep that in mind. By the way, this is uranium right here, and this would be gold, are both examples of those two, respectively. And so this is the space filling unit cell. This shows you how these atoms actually fill in this space. And you can see here that you get small portions of each of these atoms in this space. By the way, if you're paying attention, this would be 1/8 of the atom there. That would be a full one, and this would be half right there. All right, so X-ray or X-ray diffraction. So X-rays can be used to analyze different solids. They're extremely useful way to determine the structures and what solids you have. X-ray diffraction helps determine the structures of crystalline solids. Diffraction is going to occur due to the constructive interference between parallel beam waves are in phase, and that thus, because they're in phase, that means their waves line up. The constructive interference is going to actually boost that signal. And again, that's what constructive interference means, that the signal is boosted. Destructive interference happens when the waves are out of phase. That means that a peak is lined up with another wave's trough, and so they would cancel out, at least partially, and that is going to call what is called destructive interference, i.e. you're destroying the signal. Okay. By the way, X-ray diffraction, yes, X-rays are a type, are a very, very low usage X-ray diffraction. X-ray diffractions require angle and beams. They're not like the X-rays you get in hospital. Okay, same source, but not quite the same thing. So right here is what we were talking about. What you have is you have a crystalline solid right here, and these have atoms. These are the atoms right there. Actually, these are the nuclei, if you're curious. The atoms would take up more space, right? But these dots are the nuclei. So what you do is you fire off an X-ray, beam of X-rays, and these X-ray photons. Now remember, X-ray is a type of electromagnetic radiation. If you don't remember that, look back in the earlier chapters. It should be like 4 or 5-ish, depending on the book. And you will see that the electromagnetic spectrum is listed. X-rays were a very, very high energy portion of the electromagnetic spectrum. So these right here are just types of light. Okay. And so your incident rays are the ones that you fire at the solid. You fired it at an angle, and what's happening is this beam is going to have what's called coherent rays. That means that they're all the same phase. See that? They all line up when they come in. So one of the rays is going to bounce off a nucleus right there. The other ray is going to bounce off a nucleus down here. And you'll have a little bit deeper, but that's about it. You only get a few atoms in penetration. And so what's going to happen is, depending on the distance and the angle that you fired it in at, you will get constructive or destructive interference, i.e., your signal will be stronger or weaker coming out. And how you tell this, how you tell that angle, is actually the Bragg equation. So, if the sum of xy and yz gives the extra distance traveled by the lower wave, the waves will be in phase after reflection if this equation is true. So n is an integer. The wavelength is right there. That's going to be the wavelength of your x-rays. And you would have to know that wavelength going in. That's why you would select a wavelength. By the way, here's the y, x, and z's, by the way. Right here's those angles. And right here is actually the distance between the atom nuclei. So we can actually use trigonometry here. I know you may have to think really far back, but this right here is true for the, see, this is a triangle, right triangle? And so this is true for the sine of that angle times 2 times the distance would give you these two sides of that right triangle right there. And you're doing it twice, by the way, if you're curious. This is xy here, this is yz here. You're doing twice that angle right there. All right, so again, d is going to be your distance between your atom nuclei. And this right here is going to be the angle of incidence and the angle of reflection, which means the angle that you shot it at the surface and then the angle it reflected off of the surface right there. They're the same number. All right, so combining these equations together, you take 10.1 and 10.2, you substitute in, which is called variable exchange if you're ever curious, and you get this right here, which is this part and this part. All right, now this gives you something that you can actually solve in a real-world laboratory setting. You actually will know this wavelength going in, you'll know your angle of incidence, so the only thing you really need to deal with is the integer here and your distance between, which is usually what you're trying to find. So there you go. You will be able to solve that because you'll be given everything but one of these terms here. Okay, and that's Bragg's equation that you will use in a X-ray diffraction setting. We'll have some example problems, of course. Diffractometer. This is going to be used to conduct an X-ray analysis of crystals. This is actually where the diffraction comes from, X-ray diffraction. It rotates the crystal based on the X-ray beam. This collects the data produced by the scattering of the X-rays from various planes of the atoms in the crystal. It helps gather the data on bond lengths and angles of the nuclei that are involved in that crystal, that solid. Now there's two major things that you need to keep in mind when we're talking about these X-ray analysis. Number one, they always have to be done for crystals. And so you are not a crystal. Most biological compounds are not crystals when they're in the body, right? So you really do have a limitation there. Many of the things you want to study are not normally crystals. You have to be very careful that you don't take such data and go, oh, it's this way in the crystal, so it must be this way in the gas, liquid, solution, whatever. A lot of mistakes have been made because of that. But it does give you a great baseline to start from. It's like this in the crystals, so we have some clues when we get into the gas and liquid. We have something to work with. The other thing you have to be careful of is, I don't have a spectra in this notes, but if you ever saw an X-ray diffraction spectrum, my research group that I did my graduate studies with, we used to do quite a few of these and analyze these. We used to do a lot of structures. And it's like Three Peaks. it's very messy. There's not a lot to go on. It's very actually difficult to do a good job doing an X-ray diffraction to get more than a couple bond lengths and angles. So anything more complicated than basic metals and minerals and that sort of stuff becomes extremely difficult to not mess up on. And I've seen a huge number of very poorly done X-ray diffractions. It's not as easy as you might think. But for basic analysis of things like minerals, say for because somebody was murdered and you want to find out where this soil comes from, X-ray diffraction works wonderfully. It's really great for comparison purposes. So right here is an interactive example, 10.1. This uses the Bragg equation in this. So X-rays of wavelength 1.54 angstroms were used to analyze aluminum crystal. A reflection was produced at this angle right here, theta, 19.3 degrees. And so assuming n equals 1, that you're getting just the next one down, calculate the distance d between the planes of atoms producing this reflection. And so all we have to do now is we just plug this into the Bragg equation. We need to be careful about the units though, okay? Make sure you understand that your units are maintained. Also be careful about calculators. Many times a lot of you will have your calculator set to radians rather than degrees. And then you'll plug this in and get something crazy. Something completely wrong, right? So to determine the distance between the planes, we'll use that Bragg equation, of course. Our n was given to us, n equals 1. Our wavelength was given to us, 1.54 angstroms. And we were given our angle at 19.3 degrees. And so all we have to do is we just take the equation we were given before. We solve d for one side of it. That means we divide over 2 sine angle. And so we plug in our values, 1 times 1.54 divided by 2 times the sine of this angle, which is this number right here, 0.3305. By the way, notice how I do this in pieces. I get this number and I just put it there. I don't try to do this entire thing in one line in my calculator. The way you screw up and get the wrong answers all the time and miss a quarter of your questions even though you know what you're doing is you put everything in your calculator all in one line and then you forget parentheses here or multiply there or whatever and you mess up. You get wrong answers all over the place. Okay, this gives us 2.33 angstroms once we multiply all of this as our distance. Now, 2.33 angstroms is actually a correct answer. Angstroms is something you could measure distances of atoms in. An alternative unit you could use to measure these is picometers. And picometers here is just 100 times the angstrom number. Or another way of thinking that is that 1/100th, you have 100 picometers in an angstrom. Okay. So what are the types of crystalline solids? Well, of course, we have ionic solids, and these are going to possess the ions at your lattice points that will describe the structure of the solid. And so, yes, you will have salts, essentially, ionic solids, right? This is things like sodium chloride. They are crystals. You probably realized that whenever you looked at table salt, it looks like a crystal, doesn't it? So yes, it is a crystal. Molecular solids, these are going to possess discrete covalently bonded molecules at your lattice points. And these are going to be different because they will have discrete molecules at these points. Okay, so those are those covalently bonded molecules, things like water, etc. And yes, of course, water can make crystals, and that's why we get things like snowflakes, right? Atomic solids, these are going to possess atoms at the lattice points that will describe the structure of your solid. So instead of molecules, we just have atoms. at those lattice points. And of course, that is actually things like diamonds. All right, now here's examples of these. I actually used these exact ones. Apparently, I was remembering back. Here's diamond. Of course, that's a crystal. Uh, and right here we have its structure. It has carbons at its lattice points. By the way, diamond is one allotrope, one form of carbon. There's also, of course, graphite that you have in your pencil as another form of carbon. Now, this right here is sodium chloride. If you look closely at sodium chloride, it has very nice, distinct crystals that have a sort of cubic structure. By the way, if you ever want to see something that's really quite starkly beautiful and really worth sort of seeing at least once, look up crystal growth videos online, and if you do a good job searching for it, you can actually find where they've set crystal growths to music, and they're actually quite spectacular. An interesting thing, by the way, if you play music while you're growing crystals, you can actually cause the crystals to grow differently due to the vibrations. So it's kind of a neat thing. Anyways, right here we have a snowflake. It's special, and the reason it makes these snowflake patterns that we see is actually this right here, the crystal pattern of the water molecules bonding together. Of course, this being a molecular solid right here, this is an ionic solid, and this one right here is an atomic solid. All right, so let's look at the atomic solids. There's actually a bit of variety there in atomic solids. So we have metallic solids. These are going to possess a special type of delocalized, non-directional covalent bonds. You know, it's quite a bit of words, but the best way to think of metallic solids is they're like the metal atom nuclei are submerged in sort of a sea of electrons. And so they sort of share the electrons among all of the nuclei through the metal, okay? And some are more sea-like and some are more contained, less delocalized, but they don't really have a direction to the bond. They don't really have where the electrons, you can find them and go, they're between this atom and this atom. No, they just sort of flow almost freely in between the nuclei. But they are a type of covalent bond where they do share the electrons. And by the way, that's why alloys can be made of metals so easily, is because they are covalent bonds and they all have very similar electronegativities. And so yes, you can make covalent bonds between many of the metals and make metallic solids with mixtures of various types of metals. Network solids, these again possess atoms that are bonded by strong directional covalent bonds. The bonds will lead to giant molecules of these atoms. Many of these are actually single molecules that you're looking at for the entire object. Okay, so for example, this diamond right here, if it's a perfect diamond that doesn't have any fracture points in it, this could be a single molecule we're looking at the entire diamond. Lab-grown diamonds are almost always single molecules for the entire diamond. A funny thing is, diamonds are one of the places where up to a certain level of perfection, it's more expensive. And then once you get completely perfect, which is a lab-grown diamond, it drops off in price and becomes less than 1/100th of the value. So diamonds are a weird thing. Now, the group 8A solids. These are going to possess noble gas elements. They'll be attracted to each other by London dispersion forces. And so you can make crystalline solids out of the noble gases. Typically, they require extreme pressure and a very low temperature to keep them as a solid. And I used to work in a related field to this, and every single time I present, somebody would ask me about these group 8A solids, and we don't actually make solids with my research. And so I would always know exactly who's actually paying attention and who's just, popping off questions to try to look smart. All right, so Closest packing model. The closest packing arrangement is going to be characterized by layers of uniform, hard spheres that efficiently use the available space. It's literally kind of what it says, okay? It's going to essentially be that what is the structure of your solid? Well, it's going to be sort of the closest you can pack those spheres that we call that are either molecules, atoms, or ions, right? Each sphere is always going to be surrounded by 6 others. You will notice that that is distinct from our cubic cells that we talked about before. And that's because this is a different concept. They are related, but this is a different take on it. So don't get confused. Don't try to merge them in your head like many people do and, you have 2 different things occupying the same space. Types of arrangement. The 2 types of arrangement that you need to know are ABA arrangement and ABC arrangement. And we'll see pictures just here. Okay, so the ABA arrangement. There's going to be spheres in every 3rd layer that will lie directly over the spheres in the 1st layer. Think of ABA as literally like the name, because it's chemistry, everything's what the name says. You have an A layer, a B layer, and then you have another A layer, okay? And so what's going to happen is every other layer will be directly on top that 1st layer. See that? And so A will be the same as the next A, which is 3rd one. B will have another B on top of it, the other layer, every other layer. And so you'll literally just go back and forth, ABA, 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 etc., 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 stacking them up. The resulting structure is called the hexagonal closest packed, which is an HCP structure. Now, it will make sort of a hexagonal shape that sort of goes like this. The quartz crystals you see in many shops are actually a related structure. That's why they have that hexagon shape. And if you don't know what I'm talking about in quartz crystals, because for somehow you've managed to not see one of those hippie new age shops, I don't know how you could not end up seeing one of those, but Superman's crystal, okay, that he gets his Fortress of Solitude from. That's usually the one people remember for whatever reason. All right. So this is the hexagonal closest packing, and we see this from the side. Notice this would be another hexagon here, but we've cut out the part that's not in this frame. So we only have the 3 atoms or ions that would be in this frame. So right here, we turn it over and we see it from the side view. This would be your top view. We're looking down at it. And right here, this square looking thing. This right here is actually a unit cell. So this would be our unit cell right here. And you can see it's actually a face centered in this case. A cubic face centered. All right, now this right here is the ABC arrangement. So it's like the name actually says. There's not going to be any spheres in the 3rd layer that will lie on top of the 1st layer. So we'll have an A layer, a B layer that's shifted over to give the bottom part of the sphere nestled in that empty space. And then we'll have a C layer that will go on top of that. See that it occupies these spaces here. And notice that none of them overlap any of the others there. Now eventually you'll restart to again ABC again. So ABC and then you'll get another A. And this A right here will overlap on A here. B here will overlap B. C will all overlap C's. Okay? But this has 3 different layers that do not overlap, like so. This is top, of course, this is side. This is going to result in the cubic closest packed structure, which is CCP. So right here is the cubic closest packed. Again, we have excluded everything that's outside of our frame. So this is our A layer. We only have 1 atom in the frame here. We have B, C, and a layer again. We rotate it around so it matches nicely to a cube. And then we get rid of all the parts of the atoms that are, making it difficult to see. And what we can see here is this is actually our cubic structure right here. If you notice that this cube actually lines up very nicely with this unit cell right here. So that's one of the reasons why it's called cubic closest packed. Nearest neighbors of a sphere. So each sphere has 12 equivalent nearest neighbors. So if we select the middle sphere of the A, we can number these off. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and we find out there are 12 of them in the HCP here. So the net number of spheres in a face-centered cubic unit, which is of course a unit cell. A unit cell is going to be defined by the centers of the spheres on the corners of the cube. The corners or vertices always define the cube. And so that corners all have an atom, and each of those, there's only an eighth of that atom that will be inside of the cube. And so there are 8 1/8 atoms in this cube. And so that means there's a total of 1 of those atoms in this cube right here. Now, the face-centered also has all of the faces with half of an atom that's in this cube on each face. And so there are 6 faces in a cube. That means there are another 3 atoms worth of material in this cube. And so that gives us a total of 4 atoms in a face-centered cube. Or spheres in this case. By the way, I keep saying atoms. That really isn't a correct word. Spheres is the correct word. They could be molecules, of course, right? Or they could be ions. All right. So silver crystallizes in a cubic closest packed structure. The radius of silver atoms is 144 picometers. Let's calculate the density of solid silver. So right there we actually have everything we need to know except for the mass of an atom of silver, which of course we can get from periodic tables. And so what we do is the density is of course mass per unit volume. So we take mass, we divide it by volume. Typically you would do this in grams per milliliter. So the first thing I would work on is we need to know how many silver atoms will occupy a given volume in the crystal. And so the structure is cubic closest packed. That means the unit cell is going to be face-centered cubic. And so that's going to be your easiest way to deal with the volume, is to just take a cube that's going to be a face-centered cubic, figure out how big that is, figure out how many atoms of silver there are in there. Well, that number of atoms of silver is going to tell you its mass. So we must find the volume of this unit cell for silver and the net number of atoms it contains. So we need a note though, and that note is that in this structure the atoms touch along the diagonals for each face and do not along the edges of the cube. If you remember your face-centered cubic, they touch along the diagonals. See that? Like so. Alright, now the length of a diagonal would be r, the radius, plus 2 radii plus another radii. And so what we get, this would be half the length of a cell, the radius, right? Or half the length, sorry, of a sphere, or in this case, silver atom. There's 2 of them that go across in the center. There's one in the edge. There's another on the other edge. And so we get 4r, or 4 radii, as the diagonal of the cube. So we can use this fact to find the length along the edge of the cube using the Pythagorean theorem. Now let me point something out. You guys probably aren't used enough to the cubes yet that you really feel comfortable with them. But what we have here is, we know here that this cube right here has a radius right there, and then 2 radii cover this distance, and then another radius covers this. Notice that we do not know what the edges are in length because there's a gap here. We don't know what that gap is. That would be much harder to find. By the way, if you forget, you could actually draw this out and figure that out yourself. So you see that along here, right there. That's the diagonal we're talking about. Okay, and so we're going to use Pythagorean's theorem for a right angle, and we're going to find out what this diagonal is in terms of the radius of silver. And so this Pythagorean's theorem, d2 squared plus d squared equals, well, 4, this is times the radius of the silver atoms, and that would be squared. And so we solve these, get added to each other to give us 2d squared. This right here, we square 4. 4 squared is 4 times 4, 16. And we square r, and r is going to be r squared because we're not going to solve it yet. We get then divided by 2, and that gives us 8 here. We then take the square root of this, so that would be the square root of 8 times r squared. Well, the square root of something squared is going to be the same r, and then it's the square root of 8. And we don't have to solve that out right now. You can just plug it in like that. It's easier that way. So we have the r, that radius, and that was 144 picometers for a silver atom that was given to us. And so we plug that in. So 144 picometers times the square root of 8. And that will give us 407 picometers for that diagonal. All right. So now we have the unit volume of our cell is going to be, I'm sorry, this is not the diagonal, the distance, the one side of these cube. And cubes have the same distance on every side, so 407 is the distance on each side. All right, so our volume of a cube is the sides multiplied by each other, so d times d times d, or d cubed. So that's 407 cubed. That would give us 6.74 times 10 to the 7th picometers cubed. We can convert this to cubic centimeters. Cubic centimeters are the same thing as milliliters, and that's typically what you would use for a density. And so what we do is we need to convert this. So for every centimeter, there is 10 to the 10th picometers, and that's what you're seeing here. You could either write this out as 10 to the 10th picometers for 1 centimeter, or you can write it like so, where it's 1 times 10 to the negative 10th centimeters for 1 picometer. Now, we have to cube this because we need to remove 3 picometers here and replace them with 3 centimeters. So we're actually doing that 3 times. You see that? That's what that means, times this 3 times. All right, now that gives us an answer of 6.74 times 10 to the negative 23 centimeters cubed, which is also the same as milliliters or cubic centimeters. Since we know that the net number of atoms in the face-centered cubic unit cell is 4, we have 4 silver atoms contained in a volume of 6.74 times 10 to the negative 23rd centimeters cubed. Where did I get that 4? Well, I got that from the previous example where we did the math of how many spheres are in a face-centered unit cell. We just did that a few slides ago. Therefore, the density is going to be, well, you take your number of atoms times the molecular weight. Then we multiply that by the number of atoms in a mole, which is right there. That's Avogadro's number. And so you then divide it by our volume, and that gives us our density. Notice if you ever forget which parts on where put your units. Seriously, write it down, write your units down, cancel the units out. So you have atoms here, This is grams per mole. You need it to be grams on top. And so what you do is you need atoms to go away. So you put it divide by 1 mole divided by the number of atoms in a mole, which is your Avogadro's number there. And there's your volume, which is cubic centimeters or milliliters. And we have our answer, 10.6 grams per cubic centimeter. Excellent. All right, so a successful bonding model for metals must consider a few things. We have to consider what the properties we know are for metals. And so they need to be malleable. They need to have malleability. They need to have ductility, and they need to be efficient and uniform conduction of heat and electricity. So, okay. Sorry about that. I was away for a bit. Keep getting calls. All right, now we were talking about the bonding for metals. To explain this bonding and the properties of those metals, the best way to think of these is our electron C model. Okay, and so this is going to have your atom nuclei suspended in a more or less free-flowing sea of electrons, and so all your valence electrons will sort of be shared in these um, non-directional bonds, interactions, if you will, and that's actually going to do a really good job explaining the properties of the metals if you start thinking them through. Now, I want you to envision this because it'll help build up your ability to understand things and to logic out three-dimensional situations a little better. So when you envision this, envision these atom nuclei, and they have these electron clouds that they're all sharing, okay? This sea of electrons, if you will. And so if you have electrons, that's electricity, that are being put on one side of that sea of electrons. Well, they'll just jump onto the atoms that happen to be there, the atom nuclei. They'll push the electrons in that sea of electrons along that metal wire, let's say, and that will cause the electrons in the other side to come off onto, your device, your phone, your whatever. And so that actually explains the connectivity of electricity really well, because you're not actually getting the electrons you put on, they're just pushing the electrons that are already in the metal along a relatively easy, low energy sea of electron flow. And if you think about conducting heat, well, heat is going to be vibrations of your atoms. And so in a sea of electrons, the atoms can vibrate and affect each other pretty easily. So on one side, you have atoms bombarding your metal, and they cause the atoms, nuclei of the metal to start vibrating. Those vibrations will cause the next ones to also end up getting vibrated away, and they'll just transfer those vibrations along each portion of this sea of electrons with these metal atom nuclei suspended. They have more freedom to vibrate and move in that sea rather than the more strict crystalline structures we may have thought of before, where they could break things, break bonds. All right, so metal ions freely move around as the metal is hammered into it. This is malleability and ductility, by the way. If you're wondering what the difference between those is malleability is best explained by taking a wire and bending it. And so when you can bend it, thus it's malleable. That's malleability. Or you can bend a wire around, that's malleability. Ductility is you can take a piece of that metal and you can pound it into a flat sheet. And the easiest way I always find to remember this is your ducts, as in the ducts that that carry your heating and cooling in your house or your wherever you happen to be, office, library, whatever. Those ducts are usually made out of metal, right? And they're flat sheets of metal. And so ductility is literally being able to make ducts out of them. You can pound the metal into flat sheets. And metals can do this, ductility, where they pound flat without being fractured, right? They just pound out to a sheet. Many metals can also do malleability, where you can bend it back and forth without breaking it. Of course, the individual metal will have different amounts of malleability and ductility, but if you try to do that to, say, your pencil lead, you will quickly find out that your pencil lead, which is carbon, will just fracture into dust if you try to pound it out. And if you try to bend it, it'll just fracture. It won't bend almost at all. All right, so in this electron C model, remember we have these atom nuclei suspended in this sea of electrons. So if we try to bend that imaginary wire that we have with this sea of electrons with these nuclei in it, when we bend it, you'll notice that there's no directionality to the bonds. So the bonds can just shift along with the atoms. They don't have to be specifically this angle or anything like that. And so that means that when you bend it, you don't break bonds. It's still bonded and your metal's still one piece. That's kind of cool, huh? When you pound it into a sheet, that's going to, of course, just cause the electron C to flow along with the atom nuclei. They're being pounded in and then out. So again, you don't break your bonds when you pound it into a sheet. You still maintain that sea of electrons around it. And so right here we see a representation of a alkali metal, group 1, and group 2 metal on the right. And we see that this right here has a positive 1 charge, and each of these would add an electron to the sea. And this sea of electrons is going to freely pop in and out of existence around these nuclei. And it's just their presence that will keep this all bounded together. And they can freely flow around this, no problem. Right here we have group 2, and again, you see there's more electrons for the 2+ charge. So the band model or molecular orbital model. I mean, before we talked about covalent bonds make molecular orbitals, but normally we'd only talk about, 2. We talk about 2 atoms making a few molecular orbitals, right? Maybe if we're really doing a big thing, 10. Oh my goodness, that's a huge number of molecular orbitals. But now we have a molecule that could be hundreds or thousands of atoms, all with bonds to each other, that is this sea of electron bond, right? Sort of a bunch of bonds that are all overlapped on each other. And so what we have to do is we talk about these as bands. There's so many molecular orbitals that instead of looking like individual lines, they're like artistic crotch hatching, where it just looks like you're shading. It doesn't even look like individual lines. It just looks like a band of orbitals, okay? So these electrons are going to be assumed to travel around the metal crystal in bands of molecular orbitals that are so close in energy, you can't differentiate the individual ones. And here we see an example of this. So this right here would be your number of interacting atomic orbitals. So here we have 2 of them. And we see that if we look at these in terms of energy, these are going to be separated enough that we can tell the difference. If you have 4 of them, they're still separated enough that you can tell the difference. 16, they start getting kind of close, but you can tell that it's stepped. You can tell the difference between them. You can measure that okay. However, once you get something like a mole of these, and they're all interacting in a single giant molecule, if you will. Remember, a mole isn't actually that much. This is only like 100 and something grams, right? And so that really is not that much. I mean, we weigh, as humans, somewhere on the order of like 60 to 100 kilograms, right? So this really is not much weight, and you already cannot tell the difference between it. It looks like a solid band of orbitals, doesn't it? And that's because you have 10 to the 23rd of them. There's a huge number of these. They're all very close in energy, and you just can't separate them uh, enough to tell the difference. So we talk about these in bands, just like so. And so here we have our individual atoms. And when we're talking about the electrons, we can talk about them as the filled molecular orbital bands and then the empty molecular orbital bands. And so the filled ones are the ones that are going to have electrons in them. The empty molecular orbitals are going to be the ones that do not have any electrons in them, and they will be referred to as the empty MOs or the empty band. Right here, by the way, these are empty ones are always the higher energy. The lower energy will typically have the electrons in them, unless you microwave the metal, in case it'll eject electrons. And that's why your microwave gets electrocuted. Right here we have these are the 3s, by the way, and these are actually the 3p. By the way, these individual ones that we're seeing different energies for, this is your first period 1s. These are magnesium atoms, so this is 1s orbital. This is the 2s and 2p orbitals, which are the inner core electrons. These right here are the valence electrons. The valence electrons are the only ones that take part in the electron sea. The inner core doesn't do anything in bonding, electron sea or otherwise, doesn't matter. Okay, so metal alloys. So first off, an alloy is going to be a substance that contains a mixture of elements and possesses metallic properties. There are two different types of alloys that you need to know and understand. There's substitutional alloy, and really these names are so straightforward that I hope you would be able to figure them out, because most of you should know what an alloy is. I'd be a little surprised if you didn't, and at least on a basic level. And substitutional, well, if you substitute something, that means that you replace something, right? And so substitutional alloy, some of the host metal atoms will be replaced by metal atoms of a similar size. Now, let's say you tried to substitute something with something vastly different in size. Will that work? So you try to substitute a leg of your chair with something that's an inch long. Is that going to work? No, it's not going to work. Your chair is going to fall over, right? If you have a substitutional alloy, the metals have to be similar in size. They can only be a little bit different. Yeah, you could put a chair leg that's, maybe half an inch off and, it'd wobble, but okay, you can deal with that. But you can't just replace it with something completely different in size. You couldn't put in something the size of a building. You can't put in something the size of an ant. That doesn't make any sense. And so, interstitial alloys. Maybe some of you don't know what interstitial means, or maybe haven't heard the word before. Inter, as in inter, between, like interstate, internet, inter. Stitial, as in stitching, you're putting in between. And so this is an interstitial alloy. Some of the interstices in the closest packed metal structure are going to be occupied by small atoms. What this means is you have inserted small atoms in between the larger metal atoms, and they are taking up that empty space that would have otherwise been empty. And here's two great examples of these two different alloys. And so obviously this is a substitutional alloy. You see how they're similar in size. This is copper and zinc, and if you mix these two together, you'll get brass. And most of these substitutional alloys sort of have a little bit of the properties of both. And so right here you sort of get the copper resistance to corrosion and the slightly stiffer zinc and cheaper zinc, and to give you brass. Right here we see our iron and carbon, which is steel. And the greatest steel, by the way, is how much carbon you have in it. And then the types of steel, like stainless steel, that sort of thing, you would start putting other metals in there. So right here we have our interstitial alloy. And literally, carbons are just so much smaller than irons that you can put carbons in between the iron atoms. And this is actually the kind of an interesting thing, by the way. Iron is extremely hard. It's actually harder than steel. Iron also is actually quite fragile. So iron is harder, but it is not as strong. So if you were to take an iron axe, let's say, or an iron knife, and you were using it to try to cut things like a tree, uh, the iron would cut really well for a little while, and then if you hit it wrong, it would break a shard off, and a shard usually flew off and hurt somebody. And so they were actually very dangerous back in the day when they had iron axes and such. And so steel, on the other hand, is much stronger, but it's not as hard. And so if you take iron shears, you can cut steel, but the iron, instead of breaking, will flex. And these little carbons are a lot of why it does that, is because it gives pivot points for the iron to stay bonded to these carbons. And therefore it gives it more flexibility, the stronger strength of it. So, what are the influence of carbons on the properties of steel? Well, mild steel is going to contain less than 0.2% carbon. This is malleable and ductile. This is typically what you'd use for things like nails, cables, chains, that sort of stuff. Medium steel is going to contain 0.2 to 0.6% carbon. And this is actually going to be used in things like rails and structural steel beams. And you'll figure out fairly quick if you've ever played around with these. These have a lot more give to them than these do. And that's why that's medium steel. Um, anyways, right here, this is high carbon steel. It contains 0.6 to 1.5% carbon. This is very tough and hard, but it is more fragile. It isn't as strong. And so it does have better cutting edges. It's harder, flexes less, but it does have a tendency to shatter. The higher the carbon content, the more likely it is to shatter. But these are oftentimes used as springs, tools, cutlery, and that's one of the reasons, actually, if you've ever paid attention, like your knives, people break knives sometimes, and that's because it's the high carbon steel. It has better cutting edge because it's high carbon steel. Whereas, for example, it's extremely hard to snap off a nail, they just bend, and that's because it's the mild steel. All right. So network solids. These are going to be the atomic solids that contain directional covalent bonds. They'll form solids that are viewed as giant molecules. Their properties are they're typically brittle in nature. They're usually ineffective conductors of heat and electricity. Diamond is usually the stereotypical version of this network atomic solids. Each carbon atom is going to be surrounded by a tetrahedral arrangement of other carbon atoms to form a huge molecule. It's one of the hardest substances known to humanity. Technically, it's probably still the hardest substance, though there's several substances that, depending on how you do the test, different allotropes actually of diamond, that depending on how you do the test, it can break diamonds. So, yeah. An interesting side note to this is yes, diamond is very hard. Most people think diamond, well, it's hard, you can't scratch it, so it must be really great for doing things like, making armor and stuff. And you see stuff like that all the time where people think it would be really good for making knives, armor, or whatever. It's not. So if you ever take a diamond and if you took a diamond, put it on an anvil or a concrete floor, and then took a hammer to it, you can break it with your, human strength. Um, there's kind of a funny story back when I worked at UMKC in Kansas City. We had a diamond cell. It's a piece of diamond that's on a fairly large piece of steel to hold it. And the diamond's very expensive. It's $8,000 actually. Because it has to be a very, very perfect diamond. Extremely perfect. And it's fairly large as far as diamonds go. Anyways, somebody took it off to clean it, and they apparently when they were cleaning it, they didn't keep it over something, and they dropped it from chest distance down onto a concrete floor. And unfortunately, it happened to hit the diamond portion of it with the steel part pointing up towards them. And it actually broke the diamond in half. Just that drop from, chest level of a not a particularly tall man um, onto a concrete floor, not even anything super special. So diamond's actually fairly fragile as compared to something like steel. Uh, but it is very hard, yes. So this structure is going to fit the characteristics of a localized electron model. These are literally covalent bonds, just like we've talked about before, that are going to result in an extremely stable structure. Typically, these have very high melting points. They are very difficult to scratch, many of them, and they have many properties that take advantage of those covalent bonds. But on the other hand, covalent bonds are directional, and so if you hit it with force, it will fracture instead of bending. And that's why metals are so good at absorbing force, is because they will bend rather than fracture, whereas diamond will fracture. So these are actually going to be formed by those sp3 hybridized carbon atomic orbitals that we talked about before. That's what's overlapping to make a tetrahedral structure. So I know everything we learn is actually building up to make everything else easier to learn. Okay? And the more you learn, the easier it is to learn more stuff. All right. An interesting side note to this, I know I say ineffective conductors of heat and electricity. One of the things you have to realize about network solids is they are extremely dependent on the fact most of them are made with nonmetals. And nonmetals, if you remember, have wildly differing properties. So, for example, diamond actually is a very good conductor of heat. It's an excellent conductor of heat. It's a terrible conductor of electricity, but it's very good at conducting heat. And that's because when the diamond carbons vibrate, they can easily transfer the vibrations through the entire structure. An interesting side note to this also is that diamonds, network solids, have had a lot of research in recent years to substitute portions of the network solid to make them do really crazy, interesting stuff. For example, you can make semiconductors out of them. You can make that conduct electricity only some of the time, depending on what's going on. And you can do a lot of really kind of cool stuff, actually. All right, so here's your structured diamond like we saw before. So the structure according to the MO model, you have a large gap between the filled and the empty levels. You may have remembered that the metal sea of electrons, this had almost no gap, and that's why electrons can move along it so easily. It doesn't have any significant gap between filled and unfilled orbitals. And so it doesn't take any real energy for those electrons to jump around. Diamond, on the other hand, and most atomic network solids have large gaps between the filled and empty levels. And what that means is your transfer becomes very difficult. To transfer an electron from one carbon to the other and move it along the diamond, you would need to overcome a large energy gap each time. It'd be like if I told you to walk a mile and that mile was across nice flat land, that would be like metals. It doesn't have any high energy requirements to go from one side to the other. You can just walk across, right? But what happens if I put Mount Everest in between? Well, then you have to overcome that energy, right? That becomes much, much more difficult. And that's what we're talking about here. All right. Okay, so diamond is not a particularly good electrical conductor because of these large energy gaps between the filled and unfilled molecular orbitals, which of course to transfer electrons, to move electrons, electrons must occupy, be moved into those on-filled electron orbitals. Essentially, you skip from one orbital to another when you move along a substance with electricity. All right, now you can use diamond. Diamond is largely used in the industrial cutting implements. They don't actually make. Okay, so you're probably thinking in your head like a diamond scalpel or knife or something, or a little drill bit or something like that. They don't actually make the entire thing out of diamond. They take essentially pads made out of diamond. If you've ever seen like a sandpaper pad, it's like that, except it's diamond in place of sand. And then that's what they make it's a little disc essentially. That's what they make. They use diamond powder in it to make the cutting implement. Um, and it's a great way to recycle your diamond because obviously some of it gets wasted when you cut your diamonds for whatever purpose you need them. You take that diamond, you take the powder, make cutting implements. Pretty good use. Graphite can actually be converted to diamond by applying 150,000 atmospheres. For note, 1 atmosphere was the atmospheric pressure of the Earth. 30 atmospheres is enough to, you know, break pretty much anything you have in your house. And 150,000 atmospheres is huge. It's something you'd only usually find in the core of the planet. This has to be done at 2,800 degrees Celsius. Again, for reference, that is hotter than you've ever been anywhere near, I'm sure. At least I hope it would be. Would cause you some real damage. Alright, so that is very, very hot, very high pressure. There are slightly, you can reduce these energy requirements through various growth techniques, and yes, they do make laboratory diamonds. Alright, so this right here is going to be a sort of representation for you to visually understand. When you try to move electrons through something like a diamond, it's going to have your filled molecular orbitals and your empty molecular orbitals. To move electrons, which would be electricity, through this, you would have to put your electron in here. One of them would shift to the next carbon's empty molecular orbital, and you'd keep doing that over and over. And to overcome this energy gap is very difficult. It's going to take a lot of energy. So graphite, this is actually slippery. It's usually a blackish dark color. It's a conductor of heat and electricity. It is not a fantastic conductor, but it's pretty good. They've been looking at using graphite and diamonds to make semiconductors like your computers out of. Supposedly it's supposed to make them much faster. We'll see what happens. The structure is based on layers of carbon atoms. These are arranged in fused six-membered rings. The source you are probably most familiar with in terms of graphite is your pencil lead. Each carbon layer is going to be surrounded by 3 other carbon atoms in a trigonoplanar arrangement with 120-degree bond angles. This graphite has sp2 hybridization, as predicted by the localized electron model. 3 sp2 orbitals on each carbon are going to form localized bonds. These are the sigma bonds, single bonds that you're used to, with 3 other carbon atoms. 1 sp orbital on each of the carbon atoms will remain unhybridized and is going to be perpendicular to the plane. This is usually used, this is actually quite often used as lubricant in dry situations that you don't want to have grease in. And so they're used a lot in lubricants in locks, they're used a lot in lubricants in electric motors, that sort of thing. A lot of the drones have graphite lubricated, or your fans in your computers. Slipperiness is due to the strong bonding within the layers of the carbon atoms rather than between the layers. And so that's actually what you're taking advantage of when you're using your pencil lead. You're essentially rubbing it across the paper and you're causing layers to strip off of the graphite. And right here is what we mean by layers. And so right here, these are the layers of graphite. See the 3 carbons bonded together into this hexagonal arrangement. And so these layers will go across, they're just large layers. They are then not bonded. They have a weak bonding occurring between the layers. These layers is very, very weak. It's very easy to destroy. So easy that you do it whenever you wipe your pencil across a piece of paper. There you go. And that's actually what you do. You literally peel these layers off onto the paper, it deposits on the paper, and that is writing with a pencil. This is actually your sigma bonds right here between. They're in the layers. Your pi orbitals, your pi bonding network on the graphite is what helps to associate the different layers. And so they make a sort of freely flowing pi bonding network above and below each of these layers. Silicon. An important constituent of the compounds that form the Earth's crust. Many of the compounds that form the Earth's crust are silicates. Actually, a lot of them are also carbonates. We didn't really mention those, but that's okay. It's carbon with oxygens. Stable silicon compounds involve chains with silicon-oxygen bonds. For example, silica is SiO2. This is the fundamental silicon-oxygen compound. The structure of these silicon atom was going to satisfy the octet rule by forming single bonds with 4 oxygen atoms. Here, I'll just show you a picture. Okay, and so here's our SiO2s, and you see that they just form networks of bonds like that. So there's 1 Si for every O2. They form bonds as each Si forms bonds with 4 oxygens. And these are the silicates or silicas. This one is the structure of quartz actually right here, which has a higher ratio of oxygen in this case. Silicates, these are going to be compounds that are related to silica. This is based on its interconnected SiO4 tetrahedral structure. These are found typically in rocks, soils, clays. They're very common in that. But they also are what makes the sort of slippery feel of clays. So this is going to possess the O-Si ratios that are greater than 2 to 1, and they will contain silicon-oxygen anions. Cations are required to balance the excess negative charge to form neutral silicates. So if we just accounted for the SiOs, this would typically have a negative charge. So typically silicates are going to have things like sodium, potassium, etc. And these will actually make it a neutral compound overall. And so those concentrations of these trace sodium, potassium, iron, that sort of thing, cations, these are actually going to make the different colors that you normally associate with silicates, by the way. Which is why you get things like rose quartz and yellow quartz and all sorts of different silicates, or different types of glass. For example, the old red and red glass that you see in church windows from hundreds of years ago, that actually had gold in it. That was gold cations that made that color. Glass. This is going to be an amorphous solid that is formed when silica is heated above 1600 degrees Celsius and cooled rapidly. And so you notice that this right here is quartz. This has a crystalline structure. If you take silica silicates, and you um, heat them above 1600 degrees Celsius and cool them very quickly. Too fast for them to settle back in the lowest energy structure, which would be the crystal. What you will get is a glass. And glass is actually, yes, there is glass, of course, that you use in Windows. But glass is a type of substance. It's a example of an amorphous solid. For example, there's something called uh, excuse me. There's something called, well, in old days they used to call it dragon glass. Now it's onyx. It is a type of glass, and it is a black color, very shiny, quite pretty actually. People quite like it. It also has a very nasty cutting surface, which is why you get really bad cuts from glass, because you get very um, thin. Whenever it breaks, you can get very even only 1 or 2 atoms long wide cutting surfaces. Homogeneous, non-crystalline, is frozen as an almost solution looking. Think of this as disordered solid, if you will. Common glass actually results when substances such as sodium carbonate are added to the silica melt and then cooled. And that's what gives us our common glass that we see everywhere today. Uh, that is, it gives us a nice, clear, not cloudy looking glass. The properties will vary based on the additives. There's actually sort of a neat thing. You've probably heard this is called the information age, but some people actually call it the glass age, because many of the modern day electronics are based on different types of glasses that we have changed their properties to. So, two-dimensional representation of quartz crystal and quartz glass. So here we have the crystal, and right here we have the glass. And you can see this is extremely ordered, whereas this has some disorder that's introduced to it. Alright, these are some different compositions of different glasses. Um, yeah, I mean, here's the optical glass you'd see in your glasses that you wear on your face, or you'd have in telescopes and such. Um, this is normal window, which is soda lime glass. The lime is that carbonate that we were looking at. Uh, this is aluminosilicate glass that's using clickware, so it doesn't fracture when you change the heat so easily. This is the heat resistant glass. It's borosilicate that's a bit more resistant to changing temperatures. Ceramics. This can be made from clays and hardened by firing at high temperatures. Non-metallic materials that are strong, brittle, and resistant to heat and attack by chemicals. The attack by chemicals is usually their most important part and what ceramics are used most for. You'll notice they're used widely to carry out reactions in labs. They're also used widely in your to carry out reactions in your kitchen, where you cook stuff in the ceramics so that it does not react with it, which is what you're actually doing. Heterogeneous in nature, it's usually heterogeneous, as in you can see one portion versus another. You can usually see one portion versus another with your just eyes, but pretty much every ceramic you should be able to see it with a magnifying glass, or at worst, you may need a microscope. So let's look at the structure of clay. This is going to be formed by weathering action of water and carbon dioxide on the mineral feldspar. So feldspar is an aluminosilicate that weathers to form kaolinite. The kaolinite, which is consisted of tiny platelets that have this empirical formula right here, is going to, when dried, have these platelets interlocked, and that's why clay is actually kind of hard when it dries. When it's wet, the platelets will actually float around, and it makes it very slick, which is why it's actually very slippery if you get on clay when it's wet. During firing, the silicates and cations will form a glass that's going to bind the crystals of the kaolinite in a sort of matrix. So you have a glass matrix surrounding the crystals kaolinite. So ceramics are used heavily in the construction of things like jet and automobile engines. A lot of spark plugs have ceramics in them. The flexible ceramics can be obtained by adding small amounts of organic polymers. The organic polymers are going to be used to produce durable engine parts, flexible superconducting wires, and microelectronic devices and prosthetic devices. There's actually quite a wide range of uses you can make for ceramics. Part of the reason for that is you can exchange portions of this matrix to give you the properties you want in that ceramic. For example, the new non-stick surfaces you may have seen that usually are colored in a copper color are actually a titanium ceramic, and they're very, very, very difficult to react away, though they're a little bit prone to scratching. An interesting side note, by the way, the glass that they use for skyscrapers and your windshield on your car, it's very difficult to shatter that glass. However, if you take a piece of ceramic, break it so it has a sharp edge, and then throw it at that piece of glass, it will shatter. And that's because the ceramic has ceramics can make a atomic level puncturing, very, very hard edge. They actually make incredibly hard, very, very narrow puncturing and cutting edges. Semiconductors. So semiconductors, many of you, probably all of you, know that that's things like your computer chips, motherboards, things like electronics, right? Pretty much every electronic you buy nowadays has a semiconductor in it. Even things that probably don't really need it. They may have went overboard on putting semiconductors in things, honestly. But yes, pretty much everything does now. These conduct only a slight electrical current at room temperature. So semiconductors are literally what they're named. They kinda conduct electricity. So they're going to be made by something with a very specific and, let's call it, moderate gap between the occupied and unoccupied molecular orbitals. So, for example, metals had essentially no gap, right? We had diamonds that had a very large gap. Semiconductors are going to have a fairly small gap, but it still will have a gap. Okay? And so the types, there are two main types that we need to know of semiconductors. If you want to go all the way into this and you want to understand completely how a computer works on every level, let me just say it's not easy. It's very difficult. Honestly speaking, worldwide, there is nobody that can take a piece of paper and design a modern day computer circuitry. So the processor in your phone, even, there isn't a human being alive now that can just sit down and from start to finish write that out. It's just too complex now. So they actually have to work on it in parts, and they have special programs that help them. It is not easy to even understand the basic concepts of it. I'm going to give you just enough that you'll kind of think you know. And you'll have a decent enough understanding of it on the basic level. But if you want to go more into that, it's going to take quite a bit of education, okay? And some of it is actually amazingly difficult. And I'm somebody that does quantum chemistry. I literally do stuff related to rockets. And I'm saying it's pretty hard, okay? So it is an interesting field, though, and it is a huge growth field. So N-type conductors are going to be substances whose conductivity is increased by doping the element with atoms that have more valence electrons than the atoms in the host crystal. One of the ways you can help yourself remember this is N-type semiconductor, negative type. Electrons are negative. So p-type semiconductors are going to be doped with atoms that have fewer valence electrons than the atoms in the host crystal. And so one of the ways you can help yourself remember that, again, is p-type has less electrons, positive. So this substance is going to become a better conductor for being a p-type. Typically, this will lower the requirement and energy for electrons to move across that substance. A p-type and an n-type semiconductor will typically be connected in a variety of ways. The most basic one is to form a p-n junction. Really, n-type and p-type semiconductors are not particularly useful by themselves. It's the junctions that you make with them, the different structures you can make using them, that really makes these things fly. By the way, I mentioned computers for this. This is also solar panels. Solar panels are made with semiconductors as well. Also, LEDs are just another application of these same concepts. So they're all related. Okay, so the p-n type junction, this is going to make an excellent rectifier. A rectifier is going to be a device that produces a pulsating direct current from an alternating current. So this is one application you can use of these. And so here we have our energy level diagrams for an N and P type conductor, so you can better understand these. Alright, so here we have one with an excess valence electrons from our donor impurity. Again, that would be the N-type that has excess electrons. And notice that these are going to fill up part of our empty Wedgwood molecular orbitals. Another name for empty molecular orbitals, when we consider them as a whole for a large bulk application, we can call these empty molecular orbitals our conduction bands. And so, yes, it partially fills these up. Right here, we're going to have electron vacancies due to our doping atoms having less valence electrons. And so this is actually going to have this lower energy filled molecular orbitals are not going to be completely full. They're going to have empty spots that we can have electrons move into. So a p-n-type junction, a small number of electrons will migrate from an n-type region into a p-type region. Remember, the n-type region had extra valence electrons that can move into the lower energy p-type region. The contact potential prevents further migration. The contact potential is a charge buildup. So once you get a charge buildup between these two, you're going to have a barrier that will prevent further migration. And so right here, this is the charge carriers in the p-type and n-type regions. And here we have our n-type region, here we have our p-type region. Some of these electrons will move over to here into the p-type region. That's what we're seeing here. And so this is going to have a slightly negative charge because it's going to get some electrons that were not part, that are past the number of valence electrons these would normally have. And this n-type will end up with a slightly positive charge. And this is because it's losing electrons to the p-type. So, reverse and forward bias. So reverse bias, our negative is to the negative terminal of the battery, and our positive is to the positive terminal of the battery, will cause these holes in electrons to be reversed. If we have the forward bias, So this p-type is to the positive terminal of the battery. This this negatively charged n-type is to the negative terminal of the battery. What we'll see is that there is a forward bias to moving these electrons in the direction they should flow. You see that the holes here are actually moving into the n-type. The electrons are flowing out to the p-type as so. All right. That's fair. Okay, I'll go ahead and give you guys something that's a really terrible oversimplification to it, but the basics of computers and how they work are actually sort of hidden in here. And so you've noticed that we have these holes, right? Or vacancies in the molecular orbitals that don't have electrons in them. So let's look at some sort of examples. Let's say we had this right here, and we've put electrons on before. Let's say we were doing a calculation, and it had two holes in here. They're low energy, so we put on 1 plus 1. And then when we try to put the third electron, what's going to happen? Well, it's going to have a very hard time moving through here then, okay? So what would happen is that would actually give us 1 plus 1 equals 2. Okay, it's a vast oversimplification, but this gives you an idea of how how semiconductors can make digital behaviors like your computer has. And this is sort of the basics of computers. You load electrons onto the semiconductors until they modify the behavior of the semiconductor. And this modified behavior gives you your answers. Okay? And so that's how you get the 1 plus 1 equals 2, or click on here, click on there, gives you cat video. Or whatever you're looking up. I don't want to know, probably. You guys would be shocked at the number of times I get weird things sent to me by accident in a picture of your guys' screen. Please double check, by the way. All right. Okay, so molecular solids is the next part we're getting into. And this is going to be characterized by strong covalent bonding within our molecules and weak bonding between the molecules. So remember the covalent bonds, which are intramolecular forces within the molecules, the intermolecular forces between the molecules, things like London dispersion or hydrogen bonding. What exactly that intermolecular forces are is going to depend on what molecules you're looking at. Water will, of course, have hydrogen bonding. If you have something like, I'm blanking. That's pretty bad. I get interrupted so many times I forget what the hell I was talking about. Anyways, if you have some sort of dipole, those would be dipole-dipole interactions. If you have something nonpolar, it'll of course be London dispersion forces only. Don't forget, London dispersion forces are in all cases of these. So, there you go. Ionic solids, these are going to have ionic bonds between the various ions. These are very stable. They're high melting substances. They're held together by these strong electrostatic forces that exist between these oppositely charged ions. They'll literally be a positive, negative, positive, negative, positive, negative over and over and over, clinging together. Now, the structure of binary ionic solids can actually be explained by closest packing of spheres, like we talked about before. So the spheres are going to be packed to maximize that electrostatic attraction between the oppositely charged ions. But they also need to minimize the repulsions among ions with like charges. So another way of thinking of this is, yes, the plus wants to be next to the negative, but there's going to be another plus on the other side. It can't get too close to that. And so that is going to determine your structures. The types of holes in the closest packed structures is going to be these right here. So right here we have a trigonal hole. This can be formed by 3 spheres in the same layer. It's never occupied in binary ionic compounds. So binary ionic compounds, you never have anything in that hole. Tetrahedral holes are going to be formed when a sphere is located in the dimple of 3 spheres in an adjacent layer, like so. And see, it makes that tetrahedral shape again. There are twice as many tetrahedral holes as packed anions in a closest packed structure. This is an octahedral holes. This is going to be formed between 2 sets of 3 spheres and adjoining layers of the closest packed structures. The closest packed structures contain the same number of octahedral holes as packed spheres. Alright, so now we're looking at these various different types of holes and different types of structures. And so right here we see, okay, so first off, this is zinc sulfur. And one of the things you need to recognize and see is that when we're talking about ionic solids, the vertices are typically made of one ion, while the holes are packed with another ion. Or you have, see, these areas between them are packed with the zincs, whereas the sulfurs are put on the vertices and the faces, just like we saw with our face-centered cubic unit cells. Alright, so right here we have this X. It's the tetrahedral hole in the face-centered cubic unit cell. It's located right there. This is one of the tetrahedral holes that you would insert, and that's what makes this structure right here. See, that's the tetrahedral. Can you see the sort of pyramid-looking thing? There you go. Alright, so octahedral holes. This is an example of an octahedral hole. This is right here a face-centered cubic unit cell, and then you have your counter ion, which is an octahedral hole setup, which fills in like so. Okay. Alright, so let's try this out. Determine the net number of sodium and chloride ions in the sodium chloride unit cell. So the chloride ions are going to be the cubic closest packed and thus form a face-centered cubic unit cell. That's going to be your face-centered cubic unit cell. Typically speaking, the anions are much larger than the cations, and so typically speaking, the anions will be your vertices in these face-centered cubic unit cells, that sort of thing. There is a chloride ion on each corner and one at the center of each face of the cube. That's a face-centered cubic unit cell. The net number of chloride ions present in the unit cell is going to be the same as every other, the spheres, and when we talked about the face-centered unit cell. And so that's going to be 4 chloride ions per unit cell. Remember that you don't have whole chloride ions on the vertices, you only have eighths. That's where this number comes from. These are the ones on the face, which you only have half in the cube. Alright, so the sodium ions are going to occupy the octahedral holes that are located in the center of the cube and midway along each edge. The sodium ion in the center of the cube is contained entirely in the unit cell. The ones on the edge are actually shared by 4 unit cells. And so since the number of edges in a cube is 12, the net number of sodium ions present has to be 4 sodium ions as well. And so we have shown therefore that we have 4 sodium ions and 4 chlorine ions per unit cell, which hopefully is not a surprise to anybody because sodium chloride, NaCl, you should have one of each. You should have a 1-to-1 ratio. Okay? So that's good. That matches up with your sodium chloride stoichiometry. There's the math, by the way. Apparently, I got that in the wrong order. All right, so these are the types and properties of your different solids in a contained, nice little table for you to be able to, look quickly. So, some examples. Use the table 10.7. Classify each of the following substances according to the type of solid it forms: gold, carbon dioxide, lithium fluoride, and krypton. So we'll go ahead and do this. Solid gold, this is going to be an atomic solid, which means that the vertices are made out of atoms with metallic properties. Solid carbon dioxide, well, there's a big hint here. Whenever you look at these, there's one of the big hints is that if it's only an atom, if it's a pure atom, it's probably atomic, isn't it? Atom is an atomic. This right here, this is a covalent compound. These are two non-metals. And so this is typically going to be a molecular solid. This right here, well, look at this. This is lithium fluoride. That's a salt, isn't it? We have a metal and a non-metal. And so this has to be ionic. Well, we have ionic solids, so that's going to be an ionic solid, isn't it? Krypton then is another atom, if you remember. So, of course, the lithium, the solid carbon dioxide, that's going to be nonpolar carbon dioxide molecules that will be a molecular solid, held together by London dispersion forces primarily. Solid lithium fluoride is going to contain lithium and fluoride ions. This is going to be a binary ionic solid. Binary just means it's a 1-to-1 ratio. Solid krypton. This is going to contain krypton atoms. These can only interact with London dispersion forces. It is an atomic solid, but actually has properties that are characteristic of a molecular solid with non-polar molecules. Interestingly enough, krypton's kind of a weird one, and the noble gases tend to do these things. The noble gases tend to act like molecules onto themselves, especially once you get down low enough where they're fairly big. And so yes, krypton could be seen as both. I would actually say it's more like a molecular solid in the case of krypton. Alright, so a certain metal fluoride crystallizes in such a way that the fluoride ions occupy simple cubic lattice sites, while the metal atoms occupy the body centers of half the cubes. What is the formula for this metal fluoride? Alright, so what do you want to think about here? And actually, this usually is easiest if you sort of draw it out, sketch it out on a piece of paper. So you have a metal with fluoride, okay? And remember the fluorides are the F-1. Not that that particularly matters in this case. What you need to look at is in such a way that the fluoride ion occupies simple cubic lattice sites. So it's occupying the lattice sites, right? For a simple cubic, that means the corners of a cube. That's 4 on the top, 4 on the bottom. So that's a total of 8 sites that's occupying, each with an eighth in the simple cubic lattice. So while the metal atoms occupy the body centers of half the cubes. Okay, so you have 1/8 times 8, that would be 1 fluorine. These are going to have half of it in a cube, and so that would be a 1-to-2 ratio, and that would be a 1-to-2 ratio right here. So there's 2 fluorines to every 1 metal. If you're having difficulties picturing this, you might want to go back into the pictures of a simple cubic lattice, uh, sort of print it off or bring it up on another screen, and go ahead and compare what's being said here to that picture, okay? So, which of the following statements is incorrect? Ionic solids generally have high melting points. That is correct, right? You've never melted solids, have you? Or you've never melted salt, have you? When you put it in your pan, it doesn't melt. Um, Ionic solids are insulators. Well, that doesn't. Have you ever used salt to conduct electricity, or plugged in your salt wire? No, you have not, and that's because ionic solids are not great insulators. They are not really great either per se. Um, Unlike the molecular solids, are typically fairly good insulators. The binding forces in a molecular solid include London dispersion forces. Well, that's correct. Yeah. Um, did I say not good insulators? I meant not good conductors, which is what an insulator is, okay? Uh, D, molecular solids generally have high melting points. That makes sense, actually. Again, molecular solids, um, uh, molecular solids are something that you typically would boil. They're something that ice melts before room temperature. That's a molecular solid. Uh, the best way of always approaching these sorts of questions is to think about examples in your life. Okay? So, for example, we have ice that you've probably, of course, had a lot of experience with, and you have things like, of course, CO2. They're all molecular, right? They would make molecular solids. And so you know that these do not have high melting points. None of those are solid at room temperature, are they? As compared to the others. So, a certain metal fluoride catalyzes in such a way that the fluoride ions occupy simple cubic lattice sites, while the metal ions occupy the body centers of half the cubes. Alright, so in this one right here, we have a simple cubic lattice. The fluoride ions are in the simple cubic lattice sites, and so that means each of the unit cells is going to have 8 1/8, or another way of saying that would be 1 fluoride per unit cell. And then we have to figure out how many metals the unit cells would have. So while the metal ions occupy the body centers of half the unit cells. So that means that you have half a calcium every unit cell. Okay, so that means we actually have 1 calcium for every 2 fluorides. Now, fluoride has a -1 charge, or metal in this case. Sorry, we didn't know. I just jumped to the end. You have 1 metal ion, or 1 metal ion for every 2 fluorides. Fluoride has a -1 charge. That means we need to counter a -2 charge for the 2 fluorides. Now, that means that we would need something with a 2+ charge. Sodium would have a 1+ charge. If you look on your periodic table, that's group 1 again. This has a 3+ charge. That's what this right here, that Roman numeral means. This one would be a 4+ charge. Calcium is the only 2+, has to be it. Vaporization or evaporation. So molecules of a liquid are going to escape the liquid surface to form a gas. The energy required to vaporize 1 mole of this liquid at a temp pressure of 1 atmosphere is going to be called the heat of vaporization. It's represented typically by a delta H, that is a difference in enthalpy, delta H, VAP standing for vaporization. So literally this is just the symbol for heat of vaporization. This is going to be endothermic in nature because you're using up energy to break away parts of the liquid to form the gas. So it's always going to use up energy. By the way, that is what your sweat is supposed to do. It is supposed to vaporize, using up energy, being endothermic, to therefore lower the temperature of your body. The behavior of a liquid in a closed container here is going to show you an example of vaporization. And so right here at first, when we don't have any of the liquid going to vapor yet, we have an empty top of the container. And so first thing that happens is some of these molecules will gain enough energy to eject from the liquid state. And they'll go into the gaseous state. Once we have a fair number of these in the gaseous state, they're going to be bouncing around up here. And so some of them are going to bounce back when they hit the liquid. They have a fairly high chance of rejoining into the liquid. And the energy in this container is going to cause some of the liquid molecules to break off and go into the gaseous form. And this is called equilibrium. Overall, these levels don't change, but individually, these molecules, some will eject, some will go back in. Vapor pressure. So at equilibrium, the point at which no further net change occurs in the amount of liquid or vapor. The rate of condensation will equal the rate of evaporation. That's why you don't see any net change, is because the rate those two things are happening at are the same. Condensation, this is the process by which a gas becomes a liquid, whereas evaporation is going from the liquid to the gaseous state. So equilibrium vapor pressure is going to be the pressure of the vapor at equilibrium, where it reaches your equilibrium. All right, so right here is the rates of condensation and evaporation. So at first, we're going to have evaporation occurring. That's where we didn't have anything in the gaseous phase yet. Once it reaches enough molecules, what you're going to see is you get more molecules up into the vapor state. More of them can hit the liquid state and go back into the liquid state, which is condensation. So more of them can condense. And so your rate of condensation keeps going up. Eventually, they're going to equilibrize. And this is your equilibrium right here, where your rates are equal. All right, so vapor pressure, this can be measured using a simple barometer, just like you may remember from the first semester. So when the system reaches equilibrium, the vapor pressure can be determined from the change in the height of your mercury column and your barometer. So the pressure of vapor is equal to the pressure of the atmosphere minus that difference in the height. Right, here's an example. And so here we have the vacuum up here. And so this column right here is just directly telling you the atmospheric pressure, the standard atmospheric pressure being 760 torr. This right here, we have H2O. And so the vapor pressure causes this column to go down. And what that means is the difference between 760 minus what it is right here when you measure it is going to tell you the vapor pressure of the water right here, 24 torr. Same thing here, this is ethanol. You're getting the same thing. Difference tells you the vapor pressure of ethanol, and so on. All right, you have seen that water molecules has a bent shape, therefore is a polar molecule with a positively charged hydrogen, negatively charged oxygen. This accounts for many of water's interesting properties. What if the water molecule was linear instead of bent? How would this affect the properties of water, such as its surface tension, heat of vaporization, and vapor pressure? How would life be different? Because all life depends on water, right? So first off, if it wasn't bent. So you may remember CO2. CO2 is linear. The water would therefore be kind of like that, linear. And what that would mean is it would have no overall dipole because it would be linear. You'd have a positive on one end and then directly across from it, a positive charge as well. And so there is no overall dipole. And what that means is it would not hydrogen bond anymore. So you couldn't get the hydrogen bonding you've been seeing where it hydrogen bonds very nicely and very tightly and creates very strong hydrogen bonds. You would actually instead get a completely different hydrogen bonding behavior, and it could not make overall hydrogen bonds like it does. What that means is that the surface tension would be vastly lower. The heat of vaporization would be much lower as well. You could much easier boil it. In fact, water probably would not be a liquid at room temperature. It would probably be a gas at room temperature, considering its weight. The vapor pressure also would be very high. It would be much higher because it would be much easier for the water molecules to escape because it doesn't have hydrogen bonding anymore then. So how would life be different? Well, obviously if your blood did not have anything to dissolve it, instead have gas filling you, you would live a much different life. In fact, you would not be alive because that would not work. So water needs to be a liquid at room temperature. That wouldn't make any sense for living. So vapor pressure and liquids. Liquids with high vapor pressures are going to be volatile. What that means is there will be a significant portion of the liquid that will escape into the vapor phase, making a lot of that substance be in the vapor phase, thus have a high vapor pressure. That's what volatility actually means, by the way. Evaporation occurs rapidly in an open environment. So if you don't have a plug in there, something to keep it from going and leaving, gases are not contained. They don't stay in their containers. They will fill any container they are in, including rooms and the entire world, if you leave the container open. And so, yes, that would quickly cause it to evaporate. The size of the intermolecular forces in a liquid determines its vapor pressure. So the stronger the intermolecular forces in the liquid, the lower the vapor pressure because it has a harder time escaping the liquid because it has higher forces keeping it there. Substances with large molar masses have relatively low vapor pressures. Again, that's because London dispersion. Again, it has a higher it's mostly because London dispersion due to the fact that it has a higher molar mass gives it more London dispersion forces, and thus it is harder for it to break away into the vapor phase. Vapor pressure increases significantly with your temperature. So as you increase your temperature, your vapor pressure will shoot up quickly. This is actually why things boil when you get them high enough temperature. Things boil actually when their vapor pressure equals the atmospheric pressure. And that's actually the definition of boiling and boiling points. You may not remember that from last semester, but that's okay. We gave it to you again. A molecule must have sufficient kinetic energy to overcome its intermolecular forces to break away and join the vapor phase. So the vapor pressure versus the temperature. This will produce a straight line if you plot it like so. Notice that this needs to be the natural log of the pressure, the vapor pressure, equals negative delta H of the vapor, that's the enthalpy of the vaporization or heat of vaporization, over R, which is your universal gas constant, times 1 over T, that temperature right there. This is in Kelvin, by the way, because at 0 Kelvin it needs to have, well, at 0 Kelvin you can't reach it, so that's beside the point. But this is in Kelvin. Plus C, this is actually a constant that needs to be generated for that liquid. And so water will have a different one than gasoline, than water with salt in it, then it depends on the liquid you're talking about. Okay, So equation 10.4 that we just looked at right here will actually give you something that looks like a straight line. You can see it really if you look at it. This right here is your y, this is your slope, this right here, 1 over t, is your x, this right here is that plus. So of course this entire term is y, that's x, that's your slope, and this is your intercept right here, that's c. So if you were to measure these in a lab, it's actually quite easy to find out heat of vaporization and that C value for any given substance. All you have to do is you just raise the temperature, measure the temperatures, and then measure the vapor pressure as you raise that temperature. And it makes actually a pretty nice little experiment that's fairly easy to do as long as you have something that you seal very tightly. Otherwise, you have trouble. Okay, so here we have some plots. We have water, ethanol, diethyl ether, which are actually the ones we had the measurements for. If you remember back in the slide, I had the different barometers in. All right, so what we can do there is, again, that slope on these is actually the negative delta H over R. If we just are trying to determine what has the largest enthalpy of vaporizations, whether it's water or diethyl ether has a larger enthalpy of vaporization. First off, hopefully you'd be able to do this just without even looking at anything. Water is hydrogen bonding, diethyl ether is not. It's doesn't have as strong intermolecular forces. So hopefully you'd realize, oh, water probably has a larger enthalpy of vaporization. But we can actually figure that out by just taking the slope. Water has a steeper slope than the diethyl ether. That means water has a larger slope than the diethyl ether, which means the delta H for water is larger than the diethyl ether. Notice that they are all negative, and so they all go downwards, but we're just looking at the slope or how fast it does that. All right, so that leads us into the Clausius-Clapeyron equation. So when the values of delta H vaporization and the pressure of vaporization at one temperature are known, it's possible to calculate the value of pressure of vaporization at another temperature. Assume that C does not depend on temperature. We're assuming that this C value, it won't change depending on what temperature we're at. So what we can do then is each of these had that plus C. So what we do is we add over this delta H that had the 1 over T next to it. Remember that? That's this right here, to the natural log of the P vaporization for one temperature. The C will be constant, so if we have this part at one temperature equal to C, then the other temperatures will also be equal to that C. And so what we get is we get the state at one temperature versus the state at the other temperature, right there. Frankly speaking, I hate it when they name these things. They're just rearrangements of a previous equation. It's really kind of a pain in the butt. But, so we can rearrange this further to make it simplified, faster to use. You can derive it yourself if you need it now. So what we do is we take the natural logs, we subtract 1 over, we then subtract this over on the other side, so we can get the natural logs all on one side and the delta H is all on the other side. And this gives us natural log of the pressure of vaporization at the first temperature divided by the natural log of the pressure of vaporization, vapor pressure at the other temperature. And by the way, when you have a log or natural log, one log or natural log minus another log or natural log, that means that you can combine them so that the positive one is divided by the negative one. And that's what we did here. We have taken the delta H vaporization out and the over R out because they stay the same. And that leaves us with this, which is 1 over T2 minus 1 over T. By the way, if you look at this and sort of pay attention, you will notice that a very, very similar equation ends up popping up 3 or 4 times. This same sort of natural log format is actually fairly common all the way through. You'll see this in biochemistry. And so you might want to get used to these sort of forms. They're always the natural log of one state over another, and typically it's some constants. And then you have 1 over the second state minus 1 over the first state. It's sort of a common equation you see everywhere. Anyways, you may remember that from the orbitals for hydrogen, that sort of thing. The energy between the energy levels in hydrogen. Anyways, so the vapor pressure of water at 25 degrees Celsius is 23.8 torr, and the heat of vaporization of water at 25 degrees Celsius is that value right there. Calculate the vapor pressure of water at 50 degrees Celsius. Okay, so what we're going to do is we're just going to plug that into our equation, Clausius-Clapeyron equation. So we have the vapor pressure at the first temperature is that, 23.8. The temperature 1 is 25 plus 273 to give us 298 Kelvin. Don't forget this is in Kelvin. Temperature 2 then is 50 plus to give us 323 Kelvin. This right here is the heat of vaporization. You could actually theoretically, there are values of R that are in kilojoules. If you look up R on Wikipedia or something, you will end up finding 20, 30 values that are in different units. But the one you're typically going to see and be given and have available to you will be the one in joules and moles and Kelvin and usually it's atmosphere. But so this one right here is the R value. It's in joules, Kelvin, mole. This is the energy one, by the way. Careful that you don't get confused between the pressure volume one as well. All right, so here's our equation. We substitute these in right there, and then we're going to solve. Again, I would highly recommend that you solve this piecemeal. Solve that, rewrite it, solve that, rewrite it, and so on. When you do this, you're going to need to take the antilog of both sides. There's sort of two ways to do this. There is an anti-log button on many calculators, but the way I would recommend is get it down to this first, so the multiplications, additions, subtraction, do all that first. Now we're down to the logs. This is a natural log. If you just take e to the power of, it will cancel out the natural log. And you would take this side, e to the power of, and it will give you a value. And so then you'll be left with the 23.8 over that equals this number, which was e to the power of negative 1.37. And then you solve, so you cross multiply, and you got that. There we go. Okay, sublimation. It's the process in which solids change to gases without passing through the liquid state. Think of dry ice. So dry ice is the one you've probably seen before. It sublimates, so you get dry ice. It is a solid. It looks a bit like ice. That's why I call it dry ice. And it's dry because it doesn't make any liquid. It just evaporates into the gaseous phase. And so that then is sublimation. The way I like to explain it so people can remember it better is when you die, you sublimate and go off to heaven, right? That's the sort of jokey way I like to explain sublimation. and that is sublime, right? So sublimation. Iodine, by the way, also does sublimation. If you take iodine crystals, you heat them up rapidly. I don't know why they're bothering doing this with a. The way they're doing this is weird. It's completely unnecessary. But anyways, if you heat them up rapidly, they will sublime. Um, they're probably doing that to try to make it a more even spread of heat to get a better picture. Anyways, changes of state. So when we talk about changes of state, it's usually best to think of these in terms of a heating curve. And that's how I pretty much do all my changes of state in my head is you take a plot of temperature versus time for a process where the energy is added at a constant rate. So this would be like throwing a pot on burn. When a solid is heated, it will melt to form a liquid. When a liquid is heated, it will evaporate to form a vapor, right? And it has to do one after the other. You can't get a solid jumping through to a vapor unless you have sublimation. So, the heat of fusion is going to be another name for that is the enthalpy of fusion is the change in enthalpy at the melting point of a solid. So right here we see a heating curve. And they're very nice because they very graphically demonstrate heating and cooling. And the same thing does both. So if we go this direction, this is heating. So this is heating up here. We go to the right. If we want to look at cooling, we just go from the right to the left. And that's cooling. So this would be putting it on a burner. This one's putting it on a freezer. Alright, so we start down here. Below 0 degrees Celsius, which is the freezing point of water. Down here, it's going to be ice. We start adding heat, and it's going to slowly start heating up the ice from negative 20 degrees Celsius up to 0 degrees Celsius. Once it hits 0 degrees Celsius, that heat that you're adding to this isn't going to just be warming up a solid. It's actually going to start breaking the intermolecular bonds, attractions, in that ice crystal. And that will start converting that ice to liquid water. And so that's what we're seeing right here. It no longer is heating the substance up because all the energy you're adding is converting the ice, the solid, to the liquid form, which is water. And this right here, this number, directly corresponds to the heat of fusion, okay? Or heat of melting in this case, because we're melting it. So, all right, so we got our heat of fusion right there. Then once we get it into the liquid form of water, we're going to see that the heat that we're putting in is now just warming up that water. So right now it's at 0 degrees Celsius water. It's very cold water. And we're slowly going to heat that up, and it'll just get warmer and warmer. Now, once it gets up to here, it's going to start changing, breaking the bonds, and releasing those water molecules into the vapor phase. This is 100 degrees Celsius, and this is going to be the conversion of the water, liquid water, to steam, which is the vapor form of water, right? And so this right here is the heat of vaporization. This amount of energy that you're seeing in this flat line right here, that's the heat of vaporization. And it doesn't raise the temperature of the water or steam until you finish breaking all of those bonds to go into the vapor phase, steam. Once you've converted all the molecules in the vapor phase of steam, you have more energy then. The thing can then be used to increase the temperature of the steam. Now, going in the other direction, it works the exact same. This right here would be the heat of condensation then. We're just going the reverse direction, right? This right here is cooling it. And then this right here is the our heat of fusion again that's going to a solid. So, let's try a little problem here. How much energy is needed to convert 55.4 grams of ice at 0 degrees Celsius to water at 75 degrees Celsius? Okay, so I always think these problems are much, much easier if I just draw them out like so. And so what I have here is a little diagram that shows me my temperature versus energy. And I have it written in that I start at ice, which is what it says right there, at 0 degrees. And so it's 0 degrees. The first step I need to do is I need to convert my ice at 0 degrees to water, period, at 0 degrees. I'm just changing phases, ice to water. I can't increase my temperature because all my energy is going to get used up in changing phase. And so the next thing I need to do, the second step of this problem, is going to be taking the water and warming it, which is going to be taking that liquid water and going from 0 degrees Celsius to 75 degrees Celsius, which is what I'm getting right here. How do I know it needs to be liquid water first? Well, ice can't go above 0 degrees Celsius without melting. You can't get ice at 100 degrees Celsius. That doesn't work, right? When you put the ice on the oven and try to heat it up, it melts first and then you start warming up. You don't get 100 degrees Celsius ice. That doesn't work. And so, step one is going to be doing a heat of fusion problem. So I need to get my heat of fusion. So I find my heat of fusion right there. I see that this is 333 joules per gram. Now, there is an equation you could try to memorize and use. Frankly speaking, it's a giant waste of time to memorize an equation that will never, ever find any real use. The only thing you need to know is you have units. You have units that are joules per gram, right? So, what is heat? Well, heat is joules, isn't it? The energy I need is joules. I'm trying to find out energy. And so what do I need to do to this joules per gram? Well, I need to get rid of grams, don't I? Now, grams is going to be the amount of the substance here, which is in grams. So I need to multiply this 333 joules by the number of grams, 55.4 grams. By the way, if you haven't seen these before, this is called a railroad track. I tend to like to use them anytime I have something like this, which is a blank page that I used that didn't have any lines, because it helps keep everything nice and neat. The stuff on the top you multiply, so this multiplies that. The stuff on the bottom is divided, so this is divided by that and then multiplied by this. So what we have here is grams will cancel, leaving us in joules, which is what we get right there. That's the number of joules. By the way, this is what my handwriting looks like. Sorry if it's somewhat difficult to read. So the second step, we are going to heat the water. We have water now. We have 55.4 grams of water, and we need to heat it up. Well, how do we deal with heating something up? Well, if you remember back, way back in the previous semester, you were introduced to something called specific heat. Specific heat was how fast something heats up. So it's how much energy it takes to heat 1 gram 1 degree Celsius, to warm it up 1 gram 1 degree Celsius. So what we're going to do next is we have a specific heat right here for water. We only need the one for water because we are heating water at this point. You can't heat ice up to 75 degrees Celsius. It will turn into water, liquid water. So we take our specific heat of water, 4.18 joules, divided by, that's what that means, grams, degrees Celsius. I put that 1 in there just to be clear. You don't actually need the 1. Doesn't really matter. All right, so we again want energy. And so we're going to take that energy right there and we need to get it joules by itself. Okay, so we have the mass of a substance. We need to get rid of grams, so we multiply it by 55.4 grams, which is our mass of water. We also know that we need to go from 0 degrees Celsius to 75 degrees Celsius. Well, we need to get rid of the degrees Celsius there, so we have heated it by 75 degrees Celsius. So we will multiply our number by 75 degrees Celsius here. And that will cancel out degrees Celsius, giving us joules. Finally, when we do the multiplications correctly here, we get this number right here. Now, we've done 2 steps, haven't we? So what's the total energy we did in those 2 steps? Well, we just add those together. That will give us a number in joules. We can convert it to kilojoules like the answer requires, and we find out it's 35.8 kilojoules. By the way, you can usually do that in your head. You just go 1, 2, 3, and put a comma. All right. Here's another example. This just has more steps. Please try the problem first, then look at my work if you cannot figure it out on your own. Okay? You'll get a lot more bang for your buck doing that method. Alright, so this is some melting points and enthalpies of fusion for several representative solids that you've probably ran into in your time in the chemistry labs or just in general. And you can see various different melting points and enthalpies of fusion. You will notice here that the higher the melting point, typically the higher the enthalpy of fusion. That makes sense. Takes more energy to break apart. It's going to be harder to melt it, right? Alright, so here we have some the temperature at which the solid and liquid have identical vapor pressures. Right here. This is going to be the vapor pressure of the liquid, vapor pressure of the solid, and this is where they would match out. So, this shows you a solid and liquid water that can only interact through the vapor state. And if you have matching vapor pressures, they will reach an equilibrium here. So let's try this in a few different cases. So case 1, the temperature at which the vapor pressure of the solid is greater than liquid. So in this case, the solid will release a vapor that will attempt to achieve equilibrium. The liquid will attempt to achieve equilibrium by releasing a vapor as well. The net effect is going to be conversion of the solid to the liquid through the vapor phase. So this temperature would be above the melting point of the ice. In this case, by the way, since it's likely we're not at the proper pressure for this to sublimate, this is probably melting and then evaporating over here, by the way. The temperature at which the vapor pressure of the solid is, this is case 2. Part of what we're doing whenever you see these cases and me showing you previous experiments and not just telling you what it is, I oftentimes get said that, or people say things like, you only believe science, or you only believe that thing about science or that thing about chemistry because you're told to. What I'm attempting to do here, and what most chemistry professors are attempting to do, is we're attempting to give you the information to make your own conclusions so that you don't just believe whatever we tell you. You can question those conclusions and maybe make a big breakthrough later on, which would be fantastic. Some of the biggest breakthroughs in history were because a student went, hey, you gave me this information, and what about this? For example, this last month, a graduate student actually came up with a new method to test whether something's a metal, and several things that people thought were metals are not really metals. Have a less metal characteristic than they thought. So yeah, it's very important for science to progress that you actually understand how to test things, how to reason yourself, and draw your own conclusions from data. All right, so the pressure of the solid is less than that of the liquid. So in this case, the liquid will disappear and the amount of ice will increase. The solid will achieve equilibrium with the vapor. The temperature should be below the melting point of ice. Temperature and vapor pressure, case 3. So the temperature at which the vapor pressures of the solid and liquid will be identical. So they're going to coexist in this apparatus at equilibrium with the vapor exchanging back and forth, but no overall change. The normal melting point is going to be, by definition, the temperature at which the vapor pressures of the solid and liquid states are identical at 1 atmosphere of pressure. So we've worked backwards to achieve what is actually something you probably thought you already knew, but now are questioning, which is what is a melting point? Well, it's where your solid disappears and you gain liquid. But another way of looking at it, it's where the vapor pressure of your solid and liquid states are identical. In fact, melting point is where both your liquid would freeze or your solid would melt, right? So this represents the freezing point that enables the existence of a solid and liquid states at the same time. If you shift one direction away from that freezing point versus the other, that will determine whether you get solid or liquid at the end. But at the freezing point, you should have both states. Now, the normal boiling point, temperatures at which the vapor pressure of the liquid is 1 atmosphere. 1 atmosphere is special because that's the atmospheric pressure around us. That's the pressure of the atmosphere around us. So the change of states do not always occur at the boiling or melting points. Many times you're actually going to move too fast in your temperature, and you will actually get this right here, which is a dip in the temperatures. You'll get a sort of little bulge. And what that is energy can move much faster than you can form these structures, because those require the atoms or molecules to literally rearrange, right? To move. And so you may notice sound, light, all these things can travel much faster. Temperature typically can move much faster than the arrangements can happen. And so what you oftentimes get is the expected behavior is exceeded. The crystallization will actually begin down here. And this is where you'll start seeing liquid and solid. You'll have a rebound in temperature as the energy finally starts getting used, or used up or used. Now, supercooled. This is something you need to understand as well. Super meaning more than cooled. So supercooled water remains in the liquid state below 0 degrees Celsius and 1 atmosphere of pressure. This actually happens quite a bit just because oftentimes the rate at which you are cooling is actually going to be faster than the rate at which your molecules can actually arrange and move around. And so that happens quite a bit to a very small degree. It can also happen in situations where you have something preventing cooling, or purposely cool something so fast that it completely can't catch up. And that's things like flash freezing, that sort of stuff. You can get some really cool sort of behaviors by doing that. Water can also be superheated if you heat it very rapidly. And people actually do superheating a lot. So if you ever take a glass or a container with water in it, put it in the microwave and heat it, you've probably superheated your liquid before, because microwaves are pretty good at heating water. And typically if you take that out, then you will notice that it doesn't really steam at first. It sort of holds and stays with water, and then all of a sudden it'll just poof, and all of a sudden it'll just release a bunch of steam. And that's because it was superheated and then it finally vaporized. The other thing is, if it's under pressure, obviously this will happen a lot. Now this is dangerous. You do need to be careful. A lot of times people are doing this to like coffee or something they're going to put and stir stuff in. And so what happens is they do it to coffee, tea, etc. They put the spoon in while looking down in it, and it puffs and blows a bunch of hot steam in their face. And actually, people get scolded regularly on this and end up, having to seek some medical attention. Yeah, so do be careful. It's actually a fairly common thing to happen. Vapor pressure in the liquid is greater than the atmospheric pressure in the case of superheated. Bubbles will burst before reaching the surface. This will result in bumping. And so, if you've ever been heating a beaker or a pan or anything with water in it, and you notice it rocking around, it's sort of jumping around, that's what bumping is. And that's because the bubbles burst before they can reach the surface, releasing the gas, which then tries to escape throughout the entire area unevenly in the liquid, pushing the liquid around. And so that does happen quite a bit. And of course, that bottom layer would actually be superheated of the water, while the top layer usually is not. So consider the following boiling point data and decide which liquid has the highest vapor pressure at room temperature. And so we look here at these different substances and their temperatures, and that one is probably going to have the highest vapor pressure at room temperature. And that's because that one evaporates the easiest. Now, honestly, I'd be surprised if you guys even needed the temperature portion or needed this portion. You should only need one. The lowest temperature is likely to have the most in the vapor phase, right? The more of something you have, the higher the pressure it could be. So that's the most likely. This right here is diethyl ether. These other ones, hydrogen bond. And so you would expect this one to have the highest vapor pressure or otherwise be the easiest to boil, right? The most likely to go in the vapor phase. Given the graph below, what is the boiling point of carbon tetrachloride at standard pressure? And so what we're going to do here is we have to look at the graph. You don't actually need to know anything other than 4-chloride, so it's that one, and how to read a graph. So you look over here, what's the standard pressure? Well, it's 760 torr. So you trace over to our carbon tetrachloride. We're trying to find a temperature, so now we trace down, and we see it's high 70s. And right there's high 70s. So there we go. So which of the following would you expect to have the lowest vapor pressure? Well, that's probably going to be the one hydrogen bonds, right? Water. Now again, many of these questions can actually be done as long as you just, sit back and think about things that you happen to encounter in your life. And so here we have things like butane and such, right? These are things that tend to be vapors right there. This is actually butane in a lighter. This is propane, as in propane grill. This right here is ethanol. If you've ever paid attention to ethanol, you can make like volcanoes and stuff out of them. You've probably seen that at a Japanese restaurant, or you may have seen shots, fire shots before. And this, of course, has the oxygen in the middle, so that's. This is an ether, by the way, which is also tends to be gas. What is the vapor pressure of water at 7 degrees Celsius? Okay, so this one is a lot easier than you think. I know many of you are probably tempted to get the calculator out. Many of you probably grabbed your calculator, piece of paper, and were like, I'm going to really hammer this. Hopefully you didn't. Hopefully you sat back, went, hey, I can logic this, and tried to use your logic. So what is the vapor pressure at 70 degrees Celsius for water? Well, water boils at what temperature? Well, it boils at 100 degrees Celsius, right? So at 100 degrees Celsius, the vapor pressure for water has to equal the atmosphere, which is 1 atmosphere. Anything above 100 degrees Celsius, it would have to be greater than 1 atmosphere because that's greater than the boiling point. So anything below 100 has to be below 1 atmosphere. And there's only one answer there, 0.31. So we don't actually have to do any math. This right here is a phase diagram. This is a very convenient method for representing the phases of a substance as a function of temperature and pressure. You can tell a lot about a substance using this phase diagram as long as you can read it, which hopefully you will learn right here. So first we always have a solid, then we have a liquid up here, then we have a gas. How can I remember which one's which? Well, at high pressure, low temperature, things are usually solids. At higher pressure, lower temperature-ish, middle temperature, middle pressure, things tend to be liquids. And at high temperatures, low pressures, things tend to be, well, gas. And so that's the gas, liquid, solid. Right here, this is called the triple point. At this temperature and pressure, you have all three phases that are touching it. And so you would see all three phases. Right here, this is called the critical point, which I'll discuss a little bit more in a bit. Okay, so how can I read this? Well, first off, let's look at the temperatures versus pressure. So right here is 1 atmosphere. If we go across this, we can see at 1 atmosphere, which is the atmospheric pressure, 0 degrees Celsius, we have water melting. And that's true. Cool. At 1 atmosphere, 100 degrees Celsius right here, we have water going from liquid to gas. And that's called vaporization. Excellent. You will notice at that temperature and pressure, 1 atmosphere, 100 degrees Celsius, we actually have both phases, right? Liquid and gas. Here we have solid and liquid. Okay, another thing I would like to point out, let's say we had CO2. CO2 would look like this, where it has 1 atmosphere, and it goes directly from solid to gas. So what are we seeing here? Well, we're seeing that at a pressure lower than 0.006 atmospheres, which is very low, that's like a vacuum, that water will actually go from solid directly to gas, which is sublimation. We can actually get that behavior right there. All right, so we have, of course, the right here is the critical pressure and temperature. And I'll mention the critical later whenever we go on to the next slide. Right here, though, this line right here, this actually tells you something. See how it's sloped towards the solid? What that tells you is that as the pressure increases, this actually melts at a lower and lower temperature. So what that tells you is that the solid takes up more space than the liquid, or the solid in this case is actually less dense than the liquid. So if you've ever noticed, ice cubes float on top of water, and that's because the solid is less dense than the liquid. We're actually looking at water right now. And that's actually indicated right here. If it was sloping straight or it was sloping this direction, it would be the reverse, which is actually more common. Usually most liquids and solids, this line would actually be like so, which is the reverse. All right, so this is the triple point. Like I said, it's the temperature at which all three phases exist simultaneously. Critical points. This is going to be defined by a critical pressure and a critical temperature. Critical pressure is going to be the pressure that's required to produce liquefaction at the critical temperature. Critical temperature is the temperature above which vapor cannot be liquefied irrespective of the pressure applied. So what we'll see here is this actually cuts off. There is no blue line anymore after this, okay? And that's because the gas and liquid phases, you can't actually get complete liquefaction. What happens beyond this point is actually something a little strange. So beyond this point, you have a gas that's so dense, it almost looks like it's a liquid. But it is not a liquid, it is a gas, and you literally cannot get liquefaction. You cannot get those clustered structures. It's too high energy. These molecules will just be bouncing off each other everywhere. So they're very, very disordered like a gas. They're like a gas. They're just very close together. So you get some relative liquid-like behaviors. Um, the only place you're probably ever going to be able to see something like that is right after a hot spring goes off. Um, you can also sometimes see it in jets off of volcanoes, and you can see it in a reactor if a reactor ever breaks down. If you ever watch the videos of them trying to cap reactors, you'll see this spray of what looks almost like water, but goes completely to steam as soon as it gets far enough away. And those are very, very dangerous. They're very hot. They're very high pressure. Yeah, that's something. Okay, so that's the phase diagram for water. Hopefully you now know and understand how to read that. So at the melting point, again, I've done all that. You don't need any more of that. Let's talk a bit about ice skating. So in ice skating, it's kind of a cool uh, application of physics on water to give you something very neat. Ice skating, you take narrow blades and you run them across a surface of ice. And most people think that it's ice, so it's slick, so you just slide along the ice, but that's not true. The narrow blades of the skates actually exert a large amount of pressure on that ice surface that you're directly on. That frictional heat that you're causing when the skates move over that ice contributes further and causes that ice to melt. And so when you're skating, you're actually making little divots in the ice that are going to be water, is what you're actually moving across, why it's so slick. And then the ice is helping keep you on track by making a little divot. And so as the blade passes and your heat dissipates, that liquid will actually refreeze. And so if you pay very close attention, you'll start seeing swirls appear on the ice. Those are actually because of this phenomenon. And again, that's because of that phase diagram. See how it's pointed in this direction? That's because the pressure you're applying is causing it to become easier to go to the liquid. Yeah. So, kind of a cool phenomenon, huh? The low density of ice is going to cause ice to form on rivers and lakes to float. Now, this is actually going to be what keeps these bodies from completely freezing. Is the ice is going to act then as insulation around the water body. And what that means is the fish can still live below the ice because the ice is not frozen. What it also means is the ice is dangerous when it first freezes because it's just a thin layer of ice on top. It's not completely frozen. It freezes from top to bottom, not bottom to top. And so this is a relationship of boiling point and pressure. So the lower the pressure, the lower the boiling point. The easier it becomes to boil water, or really anything. And so if you're on the top of Mount Everest, you can boil water at 70 degrees Celsius. That doesn't mean it's going to be, 100 degrees Celsius when it's boiled. It still be 70 degrees Celsius, okay? So it will not be particularly hot. It will actually be a little cooler than most people like their tea when you're boiling the water. So making tea on top of Everest would be pretty hard. But here, this, for example, is Mount Whitney in California. These levels right here are about where you'd be if you're in Colorado, Wyoming. Most of Wyoming is above 6,000 feet above sea level. And so what happens is you can actually boil water much faster, but the water is only 93 degrees-ish. It's only usually 90 somethings, depending on where you are. Whereas down at sea level, you will actually see that the water will boil slower and it will actually get to 100 degrees Celsius when you're boiling it. And for example, this is below sea level right here, which is Death Valley, California, and it actually takes 100.3 to boil the water. And we already actually talked about that quite a bit, so. So this is the phase diagram for carbon dioxide. Right here you see 1 atmosphere, and that's why it sublimates, goes to the gas, at room temperature and pressure. This right here is the slope is this direction, and so yes, as you increase pressure, you're more likely to form the solid of carbon dioxide. As you increase the pressure, it takes more temperature to cause it to go liquid. All right, excellent. And so yes, the solid has a higher density than the liquid for carbon dioxide, which is more typical. Carbon dioxide is actually used in fire extinguishers. The liquid released from the extinguisher into the environment at 1 atmosphere immediately changes to vapor, which sucks in energy to fuel that phase change. And that's why it's so effective at cooling down beer. I mean, putting out fire. When I was in college, we used to take trash cans, use the fire extinguisher to cool down packets of beer in a couple minutes. If you've never tried that, make sure you put a bunch of garbage bags around it. It can make a hell of a mess. But that's how that works. That's why it's cold wherever you spray it. It's not because carbon dioxide is cold. Carbon dioxide is just a gas. It's because you're releasing the liquid, which, when it converts to vapor, sucks up a bunch of energy to do that phase change. Dry ice, that's a convenient refrigerant as it does not undergo the liquid phase. And that means you don't get under normal atmospheric conditions. And that means you don't have to deal with a liquid carbon dioxide that you have to put somewhere, right? You can just have it evaporate. It's carbon dioxide. People breathe it out all the time. Not a huge problem. On the other hand, please note that if you ever have to get carbon dioxide from a dispensary, which usually they come in like large tubs, if you have to get a bunch of it, do not reach your entire upper body in there because the container will be full of CO2. And that means you will pass out in there and someone will have to drag your butt out of it so you don't die. Okay? It is not poisonous, but it doesn't have, it's CO2. It's used up air. It's not air that you can breathe and undergo metabolism. Okay? By the way, if you ever want to try to keep dry ice, keeping it in the freezer or fridge will not work. In fact, you're better off just keeping it in the same container that you originally got it in. If you take a tightly sealed, air-sealed container and try to keep the dry ice in there, that will work best. The better an air seal you have, the better you can keep your dry ice, because then it can't go into the vapor phase because it's already at the maximum CO2 it can have in the vapor phase in there. So we talked a bit. Here's the Van der Waals equation. Van der Waals did a lot of stuff with bonding. London dispersion, by the way, can also be called Van der Waals forces. He did a lot of things with interactions and bonding. So this was developed to correct for the assumptions that we made in that kinetic molecular theory in the last semester. And our big assumption that was a bit of a failure was the ideal gas law. Remember the ideal gas law where you have vapor that you say they're too far apart to interact and they're moving too fast to interact. Well, the assumption that they don't exert forces on each other is not actually true for all cases. So Van der Waals actually added a correction factor to these pressures. And this correction factor can account for the interparticular attractions of a gas. So if you have, for say, water, they'll have a bit more interactions, and so this will have this correction factor for water. CO2 would have its own correction factor. It's fairly small. Xenon, krypton, all these things would have their own correction factors, depending on the gas. And so right here you can see these Van der Waals curves. And what you see is that if you get enough volume and a low enough pressure, you will actually cease to have to worry about van der Waals corrections. They'll go away. But if you have high pressure or a low volume, then you have to worry about your van der Waals corrections, because your van der Waals corrections will make significant issues. And this is because the base assumption that our gases are ideal and don't interact, they're based on the gas molecules being far apart. Well, if they can't get far apart, then they're going to interact. And they're based on the idea that they're not going to have time to interact. They won't be close enough together and moving slow enough to interact. Well, if you have a very high pressure, then you're going to have lots of molecules near each other, and they're going to constantly be bumping each other so they can interact. So the higher pressure, lower volume, more likely you are to need the van der Waals correction. Okay, folks, you have a great day. You take care, and good luck. Please ask me questions if anything was not clear.